In 2015, NASA scientists made a discovery that changed everything we thought about being alone in the universe. They found a planet called Kepler-452b, located 1,400 light-years away from us. What seemed to be just another distant planet turned out to be something extraordinary. It orbits a star very similar to our Sun. It takes 385 days to complete one full orbit, almost equal to our 365 days, and may have liquid water on its surface. This made scientists ask a shocking question. Could this planet, which some call Earth's older cousin, have life like ours? Prepare to sleep while listening to this video and discover the secrets of this distant world. Subscribe to the channel. Leave your like and comment from what part of the world you are watching. Get comfortable and relax. Let's begin. Have you ever wondered if there are other worlds out there similar to our own? Back in July 2015, NASA announced a discovery that would capture the imagination of people worldwide. In the vastness of space, approximately 1,400 light-years away in the constellation Cygnus, scientists found what they would come to call Earth's older cousin, an exoplanet named Kepler-452b. The discovery of Kepler-452b was the result of years of meticulous observation by NASA's Kepler Space Telescope. This remarkable instrument was designed with one primary mission: to find planets outside our solar system, particularly those that might resemble Earth. The telescope accomplished this by continuously monitoring the brightness of over 150,000 stars. When a planet passes in front of its host star, an event called a transit, it causes a tiny dip in the star's brightness. By measuring these periodic dimming events, scientists can not only detect the presence of a planet, but also calculate its size and orbit. The Kepler mission began collecting data in 2009, and by 2015, astronomers had amassed enough information to confirm the existence of this special world. The announcement on July 23rd, 2015 marked a significant milestone in our quest to find potentially habitable worlds. What made this particular discovery revolutionary wasn't just finding another planet, after all. Thousands of exoplanets had already been discovered, but rather the unique combination of characteristics that made Kepler-452b stand out from all others found before. Kepler-452b orbits a star remarkably similar to our Sun. Unlike many other potentially habitable exoplanets that orbit smaller, cooler stars called red dwarfs, the planet's star, Kepler-452 is of the same spectral type as our Sun, G2, has nearly the same temperature, and is only about 10% larger and 20% brighter. This similarity is crucial because it means the planet experiences stellar conditions not drastically different from what Earth receives from the Sun. Even more intriguing was the planet's orbit. Kepler-452b takes 385 days to circle its star, remarkably close to Earth's 365-day year. This places it firmly within what astronomers call the habitable zone, or Goldilocks zone, around its star, the region where temperatures might allow for liquid water to exist on a planet's surface. Considered essential for life as we know it, the discovery process itself was a testament to human ingenuity and technological advancement. The Kepler telescope's data required sophisticated analysis to filter out false positives and confirm genuine planetary transits. Scientists needed to observe multiple transits of the same planet to verify its existence, which meant years of continuous monitoring. For planets with longer orbital periods like Kepler-452b, this verification process took even longer, requiring patience and persistence from the research team. What made this discovery particularly challenging was the signal's subtlety. The dimming caused by Kepler-452b passing in front of its star amounted to just a fraction of a percent change in brightness. Detecting such minute variations required incredibly sensitive instruments and advanced data processing techniques to distinguish genuine planetary signals from instrumental noise and other stellar variations. The The confirmation of Kepler-452b also relied on follow-up observations using ground-based telescopes like the W. Keck Observatory in Hawaii, the Fred Lawrence Whipple Observatory in Arizona, and the McDonald Observatory in Texas. These additional observations helped to further characterize the system and rule out false positive scenarios. The revolutionary impact of finding Kepler-452b extended beyond just adding another planet to our catalogue. It provided the first real evidence that planets similar in size to Earth can exist in habitable zones around Sun-like stars. Previous discoveries had found Earth-sized planets around smaller stars, or larger planets around Sun-like stars. But Kepler-452b brought together the key elements scientists had been searching for. This discovery significantly influenced our understanding of how common potentially habitable worlds might be in our galaxy. The Kepler mission was designed to help answer this question by providing a statistical basis for estimating the frequency of Earth-like planets. Finding Kepler-452b suggested that similar planets might not be rare astronomical anomalies, but rather a relatively common occurrence throughout the Milky Way. The announcement generated excitement not just within the scientific community, but also among the general public. Media outlets around the world covered the story extensively, often referring to Kepler-452b as Earth 2... 0-inch, or Earth's cousin. The discovery tapped into humanity's age-old fascination with finding other worlds that could potentially harbour life. Scientists were careful to note that despite its promising characteristics, we still know relatively little about Kepler-452b. Its mass remains uncertain, though estimates suggest it may be about 5 times that of Earth, which would result in a significantly stronger surface gravity. Whether it has an atmosphere, oceans, or any of the other features necessary for life remains unknown and beyond the capabilities of our current technology to determine. Nevertheless, the discovery represented a profound advancement in our cosmic perspective. For centuries, humanity could only speculate about planets beyond our solar system. Then, starting in the 1990s, astronomers began confirming the existence of exoplanets, but most were gas giants unlike Earth. The progression from discovering any exoplanet at all to finding one with such Earth-like properties in just a couple of decades demonstrates the remarkable pace of advancement in this field. The Kepler mission would go on to discover thousands of exoplanet candidates before its retirement in 2018. But Kepler-452b remains one of its most significant findings. It stands as a testament to what dedicated scientific investigation can accomplish and provides a tantalizing glimpse of what future more advanced telescopes might reveal about worlds beyond our solar system. Physical characteristics and composition of Kepler-452b. Imagine a world 1.6 times the diameter of Earth, potentially rocky, orbiting a star very similar to our Sun. This is Kepler-452b, a distant exoplanet that has captivated scientists since its discovery. While we've never seen this planet directly, it's far too distant for current imaging technology. Astronomers have been able to determine several key physical characteristics that paint a fascinating portrait of this alien world. The size of Kepler-452b places it in an interesting category that astronomers often call super-Earths, or possibly mini-Neptunes. With a diameter approximately 60% larger than Earth's, it occupies a size range that doesn't exist in our solar system, where planets tend to be either roughly Earth-sized or much larger gas giants like Neptune. This intermediate size has sparked significant scientific debate about what such a planet might actually be like. Based on its size and orbital characteristics, scientists estimate that Kepler-452b has a mass approximately 5 times that of Earth. This estimate comes with considerable uncertainty, as measuring the mass of distant exoplanets is extremely challenging. The mass calculation relies on models of planetary formation and composition rather than direct measurement. If this estimate is correct, Anyone standing on the surface of Kepler-452b would experience a gravitational pull about twice as strong as what we feel on Earth. Such increased gravity would have profound implications for any life that might have evolved there, potentially resulting in shorter, stockier organisms with stronger skeletal structures. The composition of Kepler-452b remains one of the biggest unknowns and a subject of intense scientific speculation. There are essentially two main possibilities. Either it's a rocky world similar to Earth but larger, or it has a significant envelope of gases surrounding a solid core, making it more like a mini Neptune. The dividing line between these two types of planets appears to be around 1.6 Earth radii, precisely where Kepler-452b sits, making its composition particularly intriguing to scientists. If Kepler-452b is primarily rocky, it would likely have a differentiated internal structure similar to Earth's, with a metallic core, a silicate mantle, and possibly a thin crust. The larger mass could mean more internal heat retention, potentially resulting in more active geology, including enhanced volcanic activity and possibly more vigorous plate tectonics. This increased geological activity could create a more dynamic carbon cycle, which on Earth plays a crucial role in long-term climate regulation. Alternatively, if Kepler-452b has retained a substantial gaseous envelope, its surface conditions would be dramatically different from Earth's. Rather than a solid surface with continents and oceans, it might have a thick atmosphere transitioning to increasingly dense gas that eventually becomes liquid under extreme pressure. In this scenario, there wouldn't be a clear boundary between atmosphere and surface as we experience on Earth. The planet's density would provide crucial information about its composition, but unfortunately, we don't have direct measurements of Kepler-452b's density yet. For comparison, Earth has an average density of about 5.5 grams per cubic centimetre, making it the densest planet in our solar system due to its large iron core and rocky composition. Gas giants like Jupiter have much lower densities, around 1.3 grams per cubic centimetre. Where Kepler-452b falls on this spectrum would tell us a great deal about its nature. Surface conditions on Kepler-452b would be influenced by numerous factors beyond just its composition. The planet receives about 10% more light from its star than Earth does from the Sun, potentially making it somewhat warmer than our world, all else being equal. However, the planet's atmosphere would play a crucial role in determining surface temperatures through greenhouse effects and circulation patterns. If Kepler-452b does have a substantial atmosphere, its composition would be of enormous interest. Earth's atmosphere is primarily nitrogen and oxygen, but early in our planet's history, it contained more carbon dioxide and methane. Kepler-452b's atmosphere might be similar to early Earth's, or it could be dramatically different depending on the planet's evolution. The planet's stronger gravity would likely result in a thicker atmosphere extending higher above the surface than Earth's. Water is another critical factor in understanding Kepler-452b. Given its position in the habitable zone of its star, the planet could potentially maintain liquid water on its surface. If it formed with a similar water content to Earth, the distribution of water might create fascinating surface features. Some scientists speculate that planets slightly more massive than Earth might actually become water worlds, with global oceans covering their entire surfaces. Others suggest that the planet's internal heat and geological activity might create a landscape of vast mountain ranges and deep trenches, possibly with scattered seas rather than connected oceans. The day-night cycle on Kepler-452b would be similar to Earth's if the planet has a comparable rotation rate. However, many exoplanets have been found to have rotation periods very different from Earth's 24-hour day. Some planets become tidally locked to their stars, always showing the same face to their sun, creating permanent day and night sides with extreme temperature differences between them. Fortunately, given Kepler-452b's distance from its star, it's unlikely to be tidally locked, potentially allowing for a more Earth-like alternation of day and night. Seasonal patterns on Kepler-452b would depend on the tilt of its axis, something we currently have no way of measuring. On Earth, our 23.5-degree axial tilt gives us our seasons, with more direct sunlight hitting the northern hemisphere during its summer and the southern hemisphere during its summer. If Kepler-452b has a similar axial tilt, it would experience seasonal variations over the course of its 385-day year. The magnetic field of Kepler-452b is another characteristic that would significantly impact conditions on the planet. Earth's magnetic field, generated by the movement of molten iron in our outer core, protects our atmosphere from being stripped away by the solar wind. A larger, more massive planet like Kepler-452b might have a stronger magnetic field if it has a metallic core and rapid rotation, potentially providing enhanced protection for any atmosphere it possesses. Our understanding of Kepler-452b continues to evolve as astronomical techniques improve and new observatories come online. Future technologies may someday allow us to detect the composition of its atmosphere or even map major features of its surface. For now, this distant world remains tantalizingly mysterious, a planet with enough familiar characteristics to seem recognizable, yet different enough to remind us how diverse planetary systems can be throughout our galaxy. The physical characteristics of Kepler-452b tell only part of the story of this fascinating world. What makes this exoplanet particularly special is not just its composition, but where it resides in relation to its star. When astronomers describe potentially habitable worlds, they often refer to something called the habitable zone, or what some popularly call the Goldilocks zone. This concept is fundamental to understanding why Kepler-452b has generated so much excitement in the scientific community and beyond. The habitable zone represents that special region around a star where temperatures could be just right for liquid water to exist on a planet's surface. Not too hot that water would completely evaporate, and not too cold that it would remain permanently frozen, hence the Goldilocks reference. Liquid water is considered essential for life as we know it on Earth, serving as the solvent in which biological processes occur. While we can imagine forms of life using other biochemistries, water remains our primary reference point when searching for potentially habitable environments. Kepler-452b orbits comfortably within this critical zone around its star. What's particularly noteworthy is that it occupies a position in its habitable zone comparable to Earth's position in our own solar system's habitable zone. The planet receives only about 10% more stellar energy than Earth does from the Sun, placing it well within parameters where liquid water could theoretically exist. However, the habitable zone isn't simply a fixed region in space. As stars age, they gradually increase in brightness, which pushes the habitable zone outward over time. Younger stars have their habitable zones closer in, while older stars have habitable zones that have migrated outward. This dynamic nature of habitable zones has significant implications for the long-term habitability of planets. In the case of Kepler-452b, its position appears to be even more stable over long timescales than Earth's position in our solar system. The planet has potentially remained within its star's habitable zone for its entire 6 billion-year history, longer than Earth has existed. This extended period of potentially favourable conditions is particularly intriguing to astrobiologists, as it provides ample time for the potential evolution of complex life forms, assuming other necessary factors are present. It's worth noting that simply being in the habitable zone doesn't guarantee a planet will actually have liquid water or be habitable. Venus and Mars both technically lie at the edges of our Sun's habitable zone, yet neither currently supports Earth-like surface conditions. Venus suffered a runaway greenhouse effect that created a hellishly hot environment, while Mars lost most of its atmosphere and surface water over time. This demonstrates that many factors beyond orbital distance affect a planet's actual habitability. For Kepler-452b, its size and mass could actually work in favour of long-term climate stability. A more massive planet can more effectively retain its atmosphere against loss to space. If Kepler-452b formed with substantial water content and the right atmospheric composition, it might have maintained habitable surface conditions despite its star's gradual brightening over billions of years. The concept of habitable zones also extends beyond just the possibility of liquid water. Scientists sometimes refer to the UV habitable zone, where radiation levels are suitable for life, not so intense as to destroy biological molecules but sufficient to power certain chemical reactions. There's also the tidal habitable zone, where gravitational interactions between a planet and its star don't cause extreme heating of the planet's interior. Kepler-452b likely falls within these additional habitable parameters as well, further enhancing its potential for habitability. One particularly interesting aspect of Kepler-452b's position in the habitable zone relates to its star's greater age. As Kepler-452 continues to brighten over time, the habitable zone will continue to move outward. Models suggest that Kepler-452b might remain in the habitable zone for another 500 million to 1 billion years before conditions become too warm for liquid water. Or in contrast, Earth may have only about 1 billion to 2 billion years of habitable conditions remaining before our Sun's increasing luminosity pushes our planet out of the habitable zone. The stability of a habitable zone also depends on the star's behaviour. Highly active stars with frequent flares and high UV output can create challenging conditions for life, even if a planet orbits within the technically habitable zone. Fortunately, Kepler-452 appears to be a relatively stable star similar to our Sun, without extreme flaring activity that would regularly bombard planets with life-threatening radiation. The habitable zone concept has evolved significantly since it was first proposed. Early models considered only the most basic parameters of stellar radiation and planetary albedo, reflectivity. Modern habitability models now incorporate numerous additional factors: atmospheric composition and circulation, planetary rotation, ocean continent distribution, and even biological feedback mechanisms. These more sophisticated models provide a better understanding of the true potential for habitability on worlds like Kepler-452b. Another fascinating aspect of habitable zones is their width, which varies depending on the star type. Smaller, cooler red dwarf stars have very narrow habitable zones close to the star, while hotter, more massive stars have wider habitable zones located farther out. The habitable zone around Kepler-452 is relatively wide, providing some margin for error in terms of where a potentially habitable planet might orbit. Scientists have calculated that Kepler-452b has likely spent the entire 6 billion years of its existence within its star's habitable zone. This extended period of potential habitability far exceeds what was necessary for complex life to evolve on Earth. On our planet, simple life appeared relatively quickly, perhaps within the first 500 million years, but complex multicellular organisms took much longer, not appearing in abundance until less than 1 billion years ago. If life follows similar timelines elsewhere, Kepler-452b would have had ample opportunity for biological evolution to progress to advanced stages. The remarkable location of Kepler-452b in such a stable habitable zone around a Sun-like star makes it a prime target for future studies. When we consider its Earth-like orbital period of 385 days, its potentially rocky composition, and its long-term residence in the habitable zone, we can understand why astronomers consider it one of the most Earth-like exoplanets discovered to date. Despite being 60% larger than our home world, understanding Kepler-452b requires not only examining the planet itself, but also taking a closer look at its host star, Kepler-452. This distant sun shares remarkable similarities with our own star, yet its greater age provides a fascinating glimpse into what our solar system might look like in the distant future. Kepler-452 is classified as a G2 type main sequence star, the same spectral classification as our Sun. This classification indicates a yellow dwarf star with a surface temperature of approximately 5,750 Kelvin, nearly identical to our Sun's temperature. What makes this stellar twin particularly interesting is its age. Kepler-452 is estimated to be about 6 billion years old, making it approximately 1.5 billion years older than our Sun. This age difference is significant because it allows astronomers to study what happens to Sun-like stars as they continue to evolve beyond our Sun's current age. Stars like our Sun gradually increase in brightness over their main sequence lifetimes as hydrogen fusion in their cores causes changes in their internal structure. By studying Kepler-452, scientists can observe these changes directly rather than relying solely on theoretical models. The physical dimensions of Kepler-452 are remarkably close to our Sun's. Its radius is only about 10% larger than the Sun's, and its mass is estimated to be just 4% greater. These similarities make it one of the closest solar analogues ever discovered, especially among stars hosting known exoplanets. Most other exoplanet host stars differ more significantly from our Sun in terms of mass, temperature, or age. Despite these similarities, Kepler-452's greater age means it's in a slightly different phase of its evolution. The star's luminosity is approximately 20% greater than our Sun's current output. This increased brightness is a natural consequence of stellar aging on the main sequence. As hydrogen is converted to helium in the core, the star's internal temperature and pressure gradually increase, causing the star to burn hotter and shine brighter. This increased luminosity has important implications for planets orbiting Kepler-452. They receive more energy from their star than they would have earlier in the system's history. For Kepler-452b specifically, the greater stellar output is partly why the planet receives about 10% more energy than Earth gets from the Sun, despite orbiting at a distance that would be similar to Earth's in our solar system. The study of Kepler-452 provides astronomers with a valuable reference point for understanding stellar evolution. By comparing our Sun with this older but otherwise similar star, scientists can refine models that predict how our own star will change over the next billion years. These models have direct implications for Earth's future climate and habitability. Another interesting aspect of Kepler-452's age relates to its potential for stellar activity. Younger stars tend to be more active, with more frequent and intense flares, star spots, and other magnetic phenomena. As stars age, they typically become more quiescent, with magnetic activity gradually decreasing. Studies of Kepler-452 suggest it exhibits the lower activity levels expected for its advanced age, which would be favourable for the potential habitability of its planets. The metallicity of Kepler-452, its abundance of elements heavier than hydrogen and helium, also appears similar to our Sun's. This similarity in chemical composition suggests that planets forming around this star would have had access to a comparable mix of elements as planets in our solar system. Since elements like iron, silicon, carbon, and oxygen are essential building blocks for terrestrial planets and potentially for life, this shared chemistry adds another layer to the star's relevance for comparative studies. One of the most profound aspects of studying the Kepler-452 system is how it serves as a potential preview of our own solar system's future. In about 1.5 billion years, our Sun will likely reach a similar luminosity to what Kepler-452 exhibits today. By that time, Earth will be receiving significantly more solar radiation, which will intensify our greenhouse effect and potentially trigger substantial climate changes. Looking at Kepler-452b might be like looking at a future version of Earth, providing insights into how planets adapt to their evolving stars. The greater age of the Kepler-452 system also raises intriguing possibilities about potential life. If life did develop on Kepler-452b, it would have had substantially more time to evolve than life on Earth. While 6 billion years isn't dramatically longer than Earth's 4.5 billion years, those extra 1.5 billion years represent significant evolutionary time. For comparison, 1.5 billion years ago on Earth, the most complex life forms were primarily single-celled organisms, with multicellular life just beginning to emerge. The similarities between Kepler-452 and our Sun extend to their projected lifespans. Both stars are expected to remain on the main sequence for approximately 10 billion years in total before expanding into red giants. For Kepler-452, with its 6 billion year age, this means it's already about 60% through its stable lifetime, compared to our Sun at about 45% through its main sequence phase. Understanding stars like Kepler-452 helps astronomers refine their models of how frequently Sun-like stars host Earth-like planets in habitable zones. Prior to the Kepler mission, there was significant uncertainty about whether our solar system was typical or unusual in the galaxy. The discovery of systems like Kepler-452 suggests that arrangements somewhat similar to our own may not be rare cosmic accidents, but rather relatively common configurations throughout the Milky Way. The similarities between our Sun and Kepler-452 extend beyond just the stars themselves to the orbital characteristics of their planets. One of the most remarkable features of Kepler-452b is its orbital period of 385 Earth days. This period is strikingly similar to our own planet's orbital period of 365 days, differing by less than 6%. This close match is not just a cosmic coincidence, but has profound implications for the conditions that might exist on this distant world. The significance of a 385-day year begins with what it tells us about the planet's distance from its star. Kepler-452b orbits at about 1.04 astronomical units from its host star, just slightly farther than Earth's 1 astronomical unit distance from the Sun. An astronomical unit, defined as the average distance between Earth and the Sun, serves as a convenient measure when discussing planetary orbits. This placement is precisely what we would expect for a potentially habitable planet around a star slightly more luminous than our Sun. This orbital period creates a rhythm to the planet's year that would feel familiar to Earth inhabitants. If you were somehow transported to the surface of Kepler-452b, your biological clock might adapt relatively easily to the cycle of seasons, assuming the planet has an axial tilt similar to Earth's. The length of days would depend on the planet's rotation rate, which we haven't yet been able to measure, but the annual cycle would be remarkably Earth-like. The slightly longer year of Kepler-452b could mean that any seasonal changes would progress a bit more slowly than on Earth. If the planet has continents and oceans similar to Earth, these seasonal shifts could influence weather patterns, ocean currents, and potentially biological cycles in ways comparable to what we observe on our home planet. For any life that might have evolved there, this rhythm would be deeply integrated into reproductive cycles, migration patterns, or hibernation periods. What makes this orbital period particularly interesting is how it interacts with the increased luminosity of the star. As mentioned earlier, Kepler-452 is about 20% brighter than our Sun. In a simplified solar system model, this increased brightness would push the habitable zone outward. The fact that Kepler-452b orbits at a slightly greater distance than Earth does from the Sun represents a kind of cosmic balancing act, where the additional distance compensates for the star's greater brightness. The combination of orbital distance and stellar luminosity means that Kepler-452b receives about 10% more energy from its star than Earth does from the Sun. This places the planet well within the conservative boundaries of the habitable zone, but toward its inner edge. The slight increase in energy received could potentially create a somewhat warmer global climate than Earth's, assuming similar atmospheric composition and greenhouse effects. Another significant aspect of Kepler-452b's orbit is its potential stability over long periods. The orbital eccentricity, how elliptical rather than circular the orbit is, hasn't been precisely determined yet. However, if the planet's orbit is relatively circular like Earth's, it would contribute to more stable and predictable climate conditions over time. Highly eccentric orbits can cause extreme seasonal variations as a planet moves significantly closer to and farther from its star during different parts of its year. The stability of Kepler-452b's orbit over billions of years is particularly important when considering the potential for life on Earth. Relatively stable conditions over long timescales allowed life to evolve from simple single-celled organisms to the complex multicellular life we see today. Similar orbital stability on Kepler-452b would provide the consistent conditions necessary for potential biological evolution to progress through increasingly complex stages. When astronomers model the Kepler-452 system's long-term evolution, they find that Kepler-452b has likely remained continuously within the habitable zone for its entire 6 billion-year history, longer than Earth has existed. Furthermore, models suggest it will remain in the habitable zone for another 500 million to 1 billion years before its star becomes too luminous. This extended period of habitability exceeds Earth's past and future habitable lifetime, making Kepler-452b an excellent candidate for studying long-term planetary habitability. The 385-day orbit also tells us something about the formation history of the Kepler-452 system. Planets tend to form at specific distances from their stars based on where particular materials can condense in the protoplanetary disk. The similar orbital distances of Earth and Kepler-452b suggest they may have formed through comparable processes, possibly incorporating similar proportions of rocky materials and volatiles like water. This similarity adds another layer to why astronomers consider Kepler-452b to be so Earth-like despite its larger size. One fascinating implication of the planet's orbit relates to potential space exploration. If humans were ever to develop the technology for interstellar travel and visit the Kepler-452 system, astronauts would experience a year very similar in length to what they're accustomed to on Earth. This familiarity would make adapting to the new environment slightly easier, at least in terms of timing annual activities and planning long-term missions. The orbital characteristics of Kepler-452b also influence how we might one day study it in greater detail. For planets with very short orbital periods, astronomers can observe multiple transits in just a few months or years, quickly gathering data about the planet. With a longer orbital period of 385 days, Kepler-452b transits its star less frequently, meaning it takes longer to collect multiple observations. This longer period is one reason why we still have relatively limited data about this fascinating world despite its discovery in 2015. From an astronomical perspective, finding a planet with an orbital period so similar to Earth's around a Sun-like star was one of the key factors that generated excitement about Kepler-452b before this discovery. Many exoplanets found in habitable zones orbited smaller, cooler stars with orbital periods of just days or weeks rather than a full Earth year. The match between Earth's and Kepler-452b's orbital periods provided a much more direct comparison to our homeworld than had previously been possible with other exoplanets. The significance of Kepler-452b's orbital period extends beyond just its similarity to Earth's year. It represents a crucial piece in the puzzle of understanding this distant world, informing everything from its climate and seasons to its long-term habitability and potential for harbouring life. The 385-day orbit, combined with the planet's size and its position around a Sun-like star, creates a truly remarkable cosmic coincidence, a world that, despite being 1,400 light-years away, may experience annual cycles that would feel surprisingly familiar. With Kepler-452b orbiting in the habitable zone with a year-long period so similar to Earth's, the question naturally arises, could this distant world harbour liquid water on its surface? Water is the essential ingredient for life as we know it, serving as both the medium in which biochemical reactions occur and as a participant in many of those reactions. The potential for liquid water on Kepler-452b represents one of the most fascinating aspects of this exoplanet. The first and most fundamental factor supporting the possibility of liquid water is the planet's position in its star's habitable zone. As previously discussed, Kepler-452b receives about 10% more stellar energy than Earth does from the Sun, well within the range where water could remain liquid on the surface, neither completely freezing nor boiling away. This energy balance provides the basic thermal conditions necessary for a water cycle similar to Earth's. However, being in the habitable zone is just the starting point. Whether liquid water actually exists on Kepler-452b depends on numerous additional factors, beginning with whether the planet has water at all. Water is common in the universe. Hydrogen and oxygen are among the most abundant elements. And water ice is found throughout our solar system. During planetary formation, worlds that form at Kepler-452b's distance from their star typically incorporate substantial amounts of water ice that can later melt to form oceans. The planet's greater mass compared to Earth, estimated at about 5 times our planet's mass, actually works in favour of water retention. More massive planets have stronger gravity, making it harder for water molecules to escape to space. This stronger gravitational pull could allow Kepler-452b to hold onto a substantial hydrosphere even with the slightly higher stellar radiation it receives. If Kepler-452b does have water, how might it be distributed across the planet? Scientists have modelled several possibilities based on different initial water abundances and planetary characteristics. In one scenario, if Kepler-452b formed with a water content similar to Earth's, about 0.1% of its mass, it might have a surface with both continents and oceans, creating a familiar-looking landscape with coastlines, islands, and large land masses. In a second scenario, if the planet formed with significantly more water, perhaps 1 to 2% of its mass, it could be a water world with global oceans covering its entire surface. Such a planet would have no exposed continents, though underwater mountain ranges might exist. Deep ocean trenches could create varied marine environments with different pressures, temperatures, and chemical compositions. A third possibility lies between these extremes, a world with scattered smaller continents amid vast oceans covering the majority of the surface. This arrangement could create interesting climate patterns and ocean circulation systems that distribute heat from the equator toward the poles. The behaviour of water on Kepler-452b would be influenced by the planet's greater surface gravity. Waves on any oceans would likely be lower and move faster than on Earth. Rainfall might consist of smaller droplets that fall more quickly through the atmosphere. River systems would likely have different erosion patterns, perhaps creating wider, shallower channels than we typically see on Earth. The atmospheric conditions would significantly influence the planet's water cycle. A thicker atmosphere, which is likely given the planet's stronger gravity, could create stronger greenhouse effects, potentially raising surface temperatures beyond what we would expect just from the stellar energy received. This greenhouse warming could mean the difference between a mostly frozen world and one with extensive liquid oceans. Weather patterns involving water would potentially be more extreme on Kepler-452b. With more energy in the system due to the additional stellar radiation, evaporation rates could be higher, potentially creating more intense precipitation events. Storms might be larger and more powerful, driven by the additional energy and the stronger gravitational field. The chemical composition of any water on Kepler-452b might differ from Earth's oceans. Our seas contain dissolved salts and minerals that have accumulated over billions of years of interaction with crustal rocks. Depending on Kepler-452b's specific geological composition, its oceans could contain different dissolved materials, potentially creating water with different properties than Earth's. These differences could range from subtle variations in salinity to more dramatic chemical compositions depending on the planet's internal composition and geological history. If Kepler-452b has active plate tectonics, which seems plausible given its larger size and presumably greater internal heat, the interaction between water and geology could create diverse aquatic environments. Hydrothermal vents similar to those found in Earth's deep oceans might exist, potentially providing energy sources for life independent of stellar radiation. Underwater volcanic activity could enrich the oceans with minerals and create localized warm spots in otherwise cold, deep ocean environments. The long-term stability of water on Kepler-452b is particularly interesting given the planet's extended stay in the habitable zone. Earth's oceans have existed for at least 3.8 billion years, with evidence suggesting water was present even earlier. Kepler-452b's 6 billion year history within the habitable zone means any oceans there could be significantly older than Earth's. This extended timeline could have important implications for any potential biological evolution, providing ample time for complex life to develop if other necessary conditions were met. Seasonal variations in the water cycle would depend on the planet's axial tilt. If Kepler-452b has a tilt similar to Earth's 23.5 degrees, it would experience seasonal changes in precipitation and evaporation patterns. Polar regions might experience freezing and thawing cycles annually, creating seasonal ice caps that expand and contract with the 385-day year. The distribution of water would also influence the planet's climate. Oceans act as thermal regulators, absorbing heat during warm periods and releasing it during cooler times. The specific arrangement of land and water would create regional climate variations, with coastal areas experiencing milder temperature fluctuations than continental interiors. Ocean currents would distribute heat globally, potentially creating climate zones similar to Earth's tropics, temperate regions, and polar areas. If Kepler-452b has a moon or moons, as Earth does, tidal forces could create additional dynamics in any oceans, including tidal pools, environments that on Earth are thought to have played important roles in the origin of life. Strong tidal forces could also help keep any oceans mixed, preventing stagnation and helping distribute nutrients throughout the marine environment. The detection of water on Kepler-452b remains beyond our current technological capabilities. Future space telescopes might eventually be able to analyze the spectrum of light passing through the planet's atmosphere during transits, potentially revealing water vapor signatures. Such a detection would be a momentous discovery, significantly strengthening the case for Kepler-452b as a potentially habitable world. The possibility of liquid water existing on a planet orbiting a sun-like star 1,400 light-years away captures something profound about our search for places beyond Earth that might harbour life. Water represents the most basic prerequisite for life as we understand it, and finding it on worlds like Kepler-452b would suggest that the conditions for life might be relatively common throughout our galaxy. While the presence of water would be crucial for life on Kepler-452b, equally important is the nature of its atmosphere. The atmospheric composition, density, and dynamics would determine whether the planet could actually sustain liquid water and potentially support life. When scientists contemplate the possible atmosphere of Kepler-452b, they must work with models and educated speculation since direct observations remain beyond our current technological capabilities. The first consideration regarding Kepler-452b's atmosphere relates to its greater mass and gravity compared to Earth. With approximately 5 times Earth's mass and almost twice its surface gravity, Kepler-452b would likely retain a thicker atmosphere than our planet. This increased atmospheric retention ability could be significant for long-term habitability. Mars, for instance, lost most of its once thicker atmosphere partly because of its lower gravity, while Earth has managed to maintain its atmosphere for billions of years. Kepler-452b's stronger gravitational pull would make it even more efficient at holding onto atmospheric gases over geological timescales. The composition of this hypothetical atmosphere depends largely on the planet's formation history and subsequent evolution. If Kepler-452b formed similarly to Earth, its primitive atmosphere might have initially consisted primarily of hydrogen and helium captured from the protoplanetary disk. Over time, most of these light gases would have escaped to space, replaced by secondary atmospheric gases released through volcanic outgassing, primarily water vapor, carbon dioxide, and nitrogen compounds. Given the planet's location in the habitable zone, water vapor would likely be a significant atmospheric component if the planet has surface water. The water cycle would distribute moisture throughout the atmosphere, creating humidity, clouds, and precipitation patterns. The higher gravity might result in a more compressed atmospheric water cycle, with cloud formation occurring at relatively lower altitudes than on Earth. Carbon dioxide would almost certainly be present as well, released through volcanic activity. The question of how much CO2 would persist in the atmosphere depends on the planet's geological activity. On Earth, the carbon cycle regulates atmospheric CO2 through weathering of rocks, absorption by oceans, and sequestration in carbonate minerals. If Kepler-452b has active plate tectonics and liquid water oceans, similar carbon cycle processes might maintain CO2 at levels conducive to a greenhouse effect sufficient for maintaining habitable temperatures. Nitrogen could potentially form the bulk of Kepler-452b's atmosphere, as it does on Earth. Nitrogen is relatively inert, doesn't easily freeze out or react chemically under most planetary conditions, and is cosmically abundant. A nitrogen-dominated atmosphere provides a good pressure medium without contributing significantly to greenhouse warming or cooling. The presence of oxygen in substantial quantities would be particularly intriguing, as on Earth. Atmospheric oxygen is primarily a product of biological processes, specifically photosynthesis. Natural non-biological processes can produce some oxygen, but typically not in the high concentrations found in Earth's atmosphere. If future observations ever detected significant oxygen in Kepler-452b's atmosphere, it would be a tantalizing hint that photosynthetic life might exist there. Though scientists would carefully consider all possible non-biological explanations first, the atmospheric pressure at Kepler-452b's surface would likely be higher than Earth's standard pressure of 1 atmosphere. With stronger gravity compressing the gas column and potentially more total atmospheric mass, surface pressures could be several times what we experience on Earth. This higher pressure would affect many aspects of the planet's climate and potential habitability. Higher pressure raises the boiling point of water, potentially allowing liquid water to exist at higher temperatures than on Earth. It also enhances the greenhouse effect and improves atmospheric heat distribution from equator to poles. Weather patterns on Kepler-452b would be influenced by the same basic physics that drive Earth's weather, but with important differences due to the planet's unique characteristics. The slightly higher energy input from its star, combined with greater gravity and likely higher atmospheric density, could create more energetic weather systems. Storms might be more powerful, but physically smaller due to the stronger Coriolis effect from the planet's presumably similar rotation rate to Earth. Wind speeds could be lower at the surface due to greater friction from the denser atmosphere, but jet streams and upper atmospheric winds might be more powerful, driven by the larger energy gradients between equator and poles. The colour of Kepler-452b's sky would depend on the atmosphere's composition and density. If similar to Earth's atmosphere, Rayleigh scattering of sunlight would create a blue sky during the day, though perhaps a deeper blue due to the denser atmosphere. Sunsets and sunrises might display more spectacular colours due to enhanced scattering and possibly different atmospheric components. If the atmosphere contains different gases or significant quantities of suspended particles, the sky could take on other hues entirely. Protection from radiation is another crucial atmospheric function. Earth's atmosphere, particularly its ozone layer, shields surface life from harmful ultraviolet radiation from the sun. Kepler-452b would need similar protection, perhaps enhanced given that its star, being older and somewhat more luminous than our sun, likely emits slightly more UV radiation. The planet's potentially stronger magnetic field, generated by its larger, more active core, would work in conjunction with the atmosphere to deflect charged particles from stellar winds and cosmic rays. The atmospheric circulation patterns would establish the planet's climate zones. Earth has distinct tropical, temperate, and polar climate bands driven by the uneven heating of the planet from equator to poles. Kepler-452b would likely have similar broad climate zones. though their exact boundaries and characteristics would depend on factors like rotation rate, axial tilt, and distribution of land and water. With a 385-day year, seasonal shifts in these climate zones would progress at a pace very similar to Earth's. The stability of Kepler-452b's atmosphere over long timescales is particularly relevant to habitability. Our Sun has gradually increased in luminosity over billions of years, and Earth's climate has remained relatively stable, partly because feedback mechanisms in the carbon cycle have reduced atmospheric CO2 levels over time, compensating for the increasing solar output. Kepler-452b, orbiting an even older star, would need similar or perhaps more robust feedback mechanisms to maintain habitable conditions over its 6 billion year history. Clouds would play an essential role in the planet's climate, just as they do on Earth. Cloud cover reflects incoming starlight, cooling the planet, while also trapping infrared radiation, warming it. The net effect depends on cloud types, altitudes, and global distribution. On Kepler-452b, the cloud dynamics might be more complex due to the stronger gravity, higher atmospheric density, and potentially different rotation rate compared to Earth. Scientists hope that future space telescopes might be able to detect some basic properties of Kepler-452b's atmosphere. When the planet transits its star, a small fraction of starlight passes through the outer layers of the planet's atmosphere. The gases in the atmosphere absorb specific wavelengths of light, creating a spectral fingerprint that astronomers can potentially identify. The James Webb Space Telescope and other next-generation observatories aim to perform this kind of atmospheric characterization for exoplanets. Though Kepler-452b's distance and its orbit around a bright star make it a particularly challenging target, understanding the atmosphere of Kepler-452b isn't just about assessing this specific planet's habitability. It's part of a broader effort to understand how planetary atmospheres develop and evolve around different types of stars and in different regions of a planetary system. By studying worlds like Kepler-452b, scientists develop better models of atmospheric evolution that can be applied to the thousands of other exoplanets being discovered, as well as to understanding Earth's own atmospheric past and future. The challenge of characterizing Kepler-452b's atmosphere highlights both how far exoplanet science has come and how much remains beyond our grasp. Just 25 years ago, we had not confirmed a single planet beyond our solar system. Today, we're modelling the possible atmospheres of distant worlds and developing technologies that may someday tell us if these atmospheres contain the signatures of life. Beyond its atmospheric properties, Kepler-452b offers scientists something equally valuable: a window into the future of our own Earth. Because this exoplanet orbits a star older than our Sun, studying the Kepler-452 system essentially allows us to look forward in time and understand the processes of stellar evolution and their effects on orbiting planets. This perspective makes Kepler-452b an exceptional natural laboratory for understanding what might happen to our own planet billions of years from now. The star Kepler-452 is approximately 6 billion years old, roughly 1.5 billion years older than our Sun. During this additional time, the star has continued the same basic process of hydrogen fusion that powers our Sun, gradually converting hydrogen into helium in its core. As this process continues, the core slowly contracts and heats up, causing the star's outer layers to expand slightly and its overall luminosity to increase. This is why Kepler-452 is about 20% more luminous than our Sun despite having nearly the same mass. By studying Kepler-452, astronomers can directly observe what happens to Sun-like stars as they age beyond our Sun's current 4.5 billion years. The data collected helps verify and refine stellar evolution models, which previously had to rely more heavily on theoretical calculations for this phase of a Sun-like star's life. These observations confirm that the gradual brightening process occurs as predicted, with important implications for planetary habitability. The increasing luminosity of stars like our Sun creates what astronomers sometimes call the moving habitable zone problem. As a star brightens over billions of years, the habitable zone gradually shifts outward. Planets that were once comfortably within this life-friendly region can eventually receive too much stellar energy, potentially triggering runaway greenhouse effects like those seen on Venus. Meanwhile, more distant planets that were once too cold might warm to habitable conditions. Kepler-452b provides a case study in how planets respond to this gradual increase in stellar energy. Models suggest that when the Kepler-452 system was the same age as our solar system is now, about 4.5 billion years old, the planet received almost exactly the same amount of stellar energy that Earth currently receives from the Sun. Now, after an additional 1.5 billion years, it receives about 10% more energy. This increase might not sound dramatic, but even small changes in energy balance can have significant effects on planetary climate systems. Earth itself has experienced substantial climate variations throughout its history, with changes in solar input of less than 1%, combined with variations in atmospheric composition. The fact that Kepler-452b has likely maintained habitable conditions despite this increasing stellar output suggests it may have robust climate feedback mechanisms, perhaps involving the carbon cycle, cloud cover, or other processes that help regulate temperature. Looking at Kepler-452b today is essentially looking at a potential future version of Earth. In about 1.5 billion years, our Sun will reach approximately the same luminosity that Kepler-452 has now. At that point, Earth will face similar challenges to those that Kepler-452b has already encountered and apparently weathered successfully. By understanding how this exoplanet has remained potentially habitable despite its aging star, scientists might gain insights into Earth's long-term habitability prospects. The study of Kepler-452b also helps scientists understand how common long-term planetary habitability might be throughout the galaxy. If planets can routinely remain habitable for 6 billion years or more despite their star's increasing luminosity, the chances for complex life to evolve elsewhere in the universe improve significantly. Complex life on Earth took billions of years to develop, suggesting that long-term stable conditions may be necessary for advanced life forms to emerge. Another fascinating aspect of the Kepler-452 system is what it tells us about the later stages of stellar evolution that await our own Sun. After its current main sequence phase, our Sun will eventually exhaust the hydrogen in its core, causing more dramatic changes as it expands into a red giant, engulfing the inner planets. Kepler-452, being only about 1.5 billion years older, hasn't reached this phase yet, but it's closer to it than our Sun. Studying stars at various ages helps astronomers refine their models of how and when these more dramatic changes occur. The Kepler-452 system also provides insights into the long-term evolution of planetary systems as a whole. Over billions of years, planetary systems can change in various ways. Planets might migrate inward or outward due to gravitational interactions. Smaller bodies like asteroids and comets can be depleted through collisions or ejections, and the properties of any remaining debris disks can evolve. By studying older systems like Kepler-452, astronomers can better understand these long-term dynamical processes. The composition of Kepler-452 itself offers another research avenue. As stars age, their exact elemental abundances change slightly due to various processes, including gravitational settling of heavier elements. By precisely measuring the star's spectrum, astronomers can detect these subtle changes and compare them to theoretical models, further refining our understanding of stellar physics. For astrobiologists, Kepler-452b represents a particularly intriguing case study in long-term evolution of habitable conditions. If life emerged on this planet early in its history, it has potentially had up to 6 billion years to evolve, significantly longer than life on Earth. While we currently have no way of knowing if life exists there, The extended timeline makes the planet an especially interesting target in the search for complex or even intelligent life. The similarities between the Kepler-452 system and our solar system also help scientists assess how typical our own planetary system might be. Before exoplanet discoveries, we had only one example of a planetary system, our own, making it impossible to know which features were common and which might be unusual. Finding systems like Kepler-452, with potentially habitable planets orbiting Sun-like stars in Earth-like orbits, suggests that our solar system may not be especially rare in its basic architecture. Scientists are also interested in how Kepler-452b's atmosphere might have evolved over billions of years in response to its star's increasing luminosity. On Earth, the gradual brightening of the Sun has been partially offset by a slow decline in atmospheric greenhouse gases, particularly carbon dioxide, through geological processes. Similar processes might have occurred on Kepler-452b, potentially offering lessons about how planetary atmospheres naturally adapt to changing stellar conditions. The older age of the Kepler-452 system might also provide insights into long-term geological evolution. Earth's geological activity has gradually declined over billions of years as its interior slowly cools. Kepler-452b, being both older and more massive than Earth, might show different patterns of geological aging. Its larger size could mean more retained internal heat and potentially more enduring geological activity, despite its greater age. The study of Kepler-452b in the context of stellar evolution connects to broader questions about the long-term habitability of planets throughout the galaxy. As we discover more exoplanets around stars of different ages, we can begin to construct a more complete picture of how habitability evolves over time. This research has implications not just for understanding distant worlds, but for anticipating Earth's own distant future as our Sun continues to brighten. The insights gained from studying Kepler-452b and its star illustrate the value of exoplanet research beyond the simple thrill of discovery. These distant worlds serve as natural experiments, showing us variations on planetary evolution that we could never observe in our own solar system alone. Each new system we study, particularly those with different ages, adds another data point to our understanding of how stars and planets change together over cosmic timescales. The study of exoplanets like Kepler-452b is as much a story about technology as it is about the planets themselves. The methods we use to detect and study these distant worlds reveal both the ingenuity of modern astronomy and the significant limitations we still face. Kepler-452b was discovered using what's called the transit method, which has become the most prolific technique for finding exoplanets, but comes with important constraints that shape our understanding of this distant world. The transit method works on a simple principle. When a planet passes directly between its star and our telescopes, it blocks a tiny fraction of the star's light, causing a measurable dip in brightness. The Kepler Space Telescope, launched by NASA in 2009, was specifically designed to detect these minute changes in stellar brightness. For 4 years, it continuously monitored over 150,000 stars in a single patch of sky, looking for the telltale periodic dimming that would indicate an orbiting planet. What makes this method challenging is just how small these brightness changes are. When Kepler-452b transits its star, it blocks only about 0.01% of the star's light, a change so subtle that it would be impossible to detect with ground-based telescopes for this particular star. The Kepler telescope's extraordinary precision, combined with its position in space above the distorting effects of Earth's atmosphere, made such detections possible. The transit method also requires a specific geometric alignment. We can only detect planets whose orbital planes are aligned with our line of sight to their star. For a planet in an Earth-like orbit, the probability that its orbit is aligned properly for us to see transits is less than 1%. This means that for every transiting planet we discover, there may be more than 100 similar planets that we miss simply because their orbital planes are tilted relative to our viewpoint. This geometric requirement has significant implications for our understanding of planets like Kepler-452b. We're only seeing a small subset of the total population of such worlds, which means they're likely much more common than the raw numbers of discoveries would suggest. Statistical analyses of Kepler data indicate that potentially habitable planets around Sun-like stars might exist around roughly 10 to 20% of such stars in our galaxy. Another limitation of the transit method is that it primarily tells us about a planet's size, not its mass or composition. When astronomers announced the discovery of Kepler-452b in 2015, they could confidently state its diameter, about 60% larger than Earth's, based on how much starlight it blocked. But they could only estimate its mass based on theoretical models rather than direct measurement. To directly measure an exoplanet's mass, astronomers typically use the radial velocity method, which detects the tiny wobble of a star caused by the gravitational pull of an orbiting planet. For distant stars like Kepler-452, however, this wobble is extremely difficult to measure with current technology. The star is too faint, and the expected signal too small, for even our most sensitive instruments to detect reliably. This is why there remains some uncertainty about whether Kepler-452b is a rocky super-Earth or a gaseous mini-Neptune. The vast distance to the Kepler-452 system, approximately 1,400 light-years, creates additional challenges. At such distances, we have no hope of directly imaging the planet with current or near-future technology. Direct imaging of exoplanets has been achieved, but generally only for young, massive planets orbiting far from their stars, a very different scenario from Kepler-452b. This distance also means we receive very little light from the system, making detailed follow-up observations extremely difficult. The star itself is about 21st magnitude, about 10 million times fainter than what can be seen with the naked eye, requiring large telescopes for even basic studies. The timescale of Kepler-452b's orbit presents another practical challenge. With a year lasting 385 Earth days, astronomers need many years of observations to capture multiple transits and confirm the planet's existence. The original Kepler mission observed the star for only 4 years, capturing just enough transits to confirm the discovery, but limiting how much data was available for detailed analysis. Future technological developments may eventually overcome some of these limitations. The James Webb Space Telescope, launched in late 2021, offers unprecedented infrared sensitivity that could potentially detect thermal emission from the planet or analyze starlight filtered through its atmosphere during transits. However, even this next-generation observatory will be challenged by the faintness of the star and the relatively small signal produced by the planet. Ground-based extremely large telescopes currently under construction, with primary mirrors 30 meters or larger, might eventually contribute to characterizing the Kepler-452 system. These massive instruments will collect enough light to perform more detailed spectroscopic studies of the star, potentially even detecting the radial velocity signal of Kepler-452b to determine its mass. More advanced future missions, like the conceptual Large UV/Optical/IR Surveyor, LUVOIR, or Habitable Worlds Observatory being considered by NASA, could potentially have the capability to directly image planets like Kepler-452b and analyze their atmospheric composition in detail. However, such missions remain at least a decade or two away from reality. These technological limitations highlight an important aspect of exoplanet research. Our understanding evolves not just as we discover more planets, but as our tools for studying them improve. The first exoplanet around a Sun-like star was only discovered in 1995, and the field has advanced remarkably in less than 3 decades. Technologies that seemed impossible a generation ago are now being developed or deployed. The story of Kepler-452b's detection also illustrates the incremental nature of astronomical discovery. The planet was found in data collected years earlier, after careful analysis and verification. Even now, Scientists continue to refine their understanding of this system as new analytical techniques are applied to the existing data and as additional observations are made. Despite these limitations, the methods used to discover and study Kepler-452b represent a remarkable achievement. Just 50 years ago, the very existence of planets beyond our solar system remained in the realm of speculation. Today, we can detect a planet similar in size to Earth, orbiting in the habitable zone of a Sun-like star, at a distance of 1,400 light-years, a testament to human ingenuity and our drive to understand the cosmos. The current technological limitations in studying Kepler-452b also serve as motivation for developing the next generation of astronomical instruments. Each new discovery raises questions that current technology cannot fully answer, spurring innovation and investment in more powerful observatories. This cycle of discovery and technological advancement has characterized astronomy throughout history and continues to drive the field forward today. Kepler-452b stands as just one example of the thousands of exoplanets discovered to date, each offering its own scientific insights. When comparing this world to other promising exoplanets, we gain a broader perspective on the diversity of potentially habitable environments that exist beyond our solar system. Since the first exoplanet discovery around a Sun-like star in 1995, astronomers have found an astonishing variety of worlds, from gas giants larger than Jupiter orbiting closer to their stars than Mercury does to our Sun, to small rocky planets in multi-planet systems. Among these thousands of discoveries, a small subset has generated particular excitement for their potential habitability. How does Kepler-452b compare to these other promising worlds? Perhaps the most famous system of potentially habitable exoplanets is TRAPPIST1, located about 40 light-years from Earth, discovered in 2016. This system contains 7 roughly Earth-sized planets orbiting a tiny red dwarf star. At least 3 of these planets, TRAPPIST1e, F, and G, orbit within their star's habitable zone. What makes the TRAPPIST-1 planets different from Kepler-452b is primarily their star. TRAPPIST-1 is much smaller, cooler, and redder than our Sun, with only about 8% of the Sun's mass. This means that even though these planets receive potentially habitable levels of energy, the quality of that energy is very different, more concentrated in infrared wavelengths rather than visible light. Another key difference is proximity, both to Earth and to each other. At just 40 light-years away, the TRAPPIST-1 planets are much closer to us than Kepler-452b, making them easier to study in detail. They're also much closer to each other in their orbital arrangement. While Kepler-452b takes 385 days to orbit its star, the TRAPPIST-1 habitable zone planets have years lasting just 6 to 12 Earth days, orbiting much closer to their cooler star. Proxima Centauri b represents another important comparison case. Discovered in 2016, this planet orbits the closest star to our Sun, Proxima Centauri, just 4.2 light-years away. Like the TRAPPIST-1 planets, Proxima b orbits a red dwarf star much smaller and cooler than our Sun. The planet is roughly Earth-sized and receives an amount of energy that could allow for liquid water on its surface. The proximity of Proxima b makes it an exceptional target for future studies and even potential interstellar missions. However, its star poses significant challenges for habitability. Proxima Centauri is a highly active star that regularly produces powerful flares, bombarding its planet with high-energy radiation that could strip away its atmosphere over time and potentially sterilize its surface. TOI 700d, discovered by NASA's TESS mission in 2020, represents yet another type of potentially habitable world. This planet is almost exactly Earth-sized and orbits within the habitable zone of its star, a small red dwarf about 100 light-years from Earth. Like the other red dwarf planets mentioned, XY700d orbits much closer to its star than Earth does to the Sun, completing an orbit in just 37 days. What distinguishes Kepler-452b from these other promising exoplanets is primarily its star. While the majority of potentially habitable exoplanets discovered so far orbit red dwarf stars, Kepler-452b orbits a G-type star remarkably similar to our Sun. This stellar similarity makes Kepler-452b especially valuable for comparison to Earth, as it experiences similar types of stellar radiation and has an orbital period close to our own year. The importance of the star type cannot be overstated when considering planetary habitability. Red dwarf stars pose several challenges for their planet's habitability. They emit more damaging flares and radiation. Their habitable zones are so close that planets there likely become tidally locked, always showing the same face to their star. And the different spectrum of light they emit might affect potential photosynthesis and other biological processes. Kepler-452b avoids many of these red dwarf challenges by orbiting a Sun-like star. Its greater distance from Earth compared to systems like TRAPPIST-1 or Proxima Centauri means we currently know less about it. But its solar system arrangement makes it more directly comparable to Earth than planets orbiting very different types of stars. Another distinction is Kepler-452b's size, at 1.6 times Earth's diameter. It's larger than most of the potentially habitable planets mentioned above, which tend to be closer to Earth's size. This larger size places Kepler-452b at the boundary between rocky super-Earths and gaseous mini-Neptunes, raising questions about its true nature that don't apply to more clearly Earth-sized worlds. The age of the Kepler-452 system also sets it apart from many other discoveries. At approximately 6 billion years old, it's significantly older than our solar system and most other well-studied exoplanet systems. This greater age provides a longer potential timeline for biological evolution, if life ever arose there, and demonstrates long-term planetary system stability. When scientists compare these various potentially habitable exoplanets, they're not just ranking them by habitability. Each different planetary system provides unique insights into planet formation and evolution under different conditions. Red dwarf planets teach us about habitability around the most common type of star in our galaxy. Planets like Kepler-452b show us how Earth-like planets might develop around Sun-like stars. The diversity of these discovered worlds also helps astronomers refine their understanding of how common potentially habitable planets might be throughout our galaxy. By finding habitable zone planets around different types of stars, at various distances and with different properties, scientists can make better statistical estimates of the total population of such worlds. This comparative approach has revealed that potentially habitable planets appear to be common in our galaxy, perhaps averaging at least one per star, though with considerable variation in their specific properties. The discovery of Kepler-452b and worlds like it suggests that planets in Earth-like orbits around Sun-like stars aren't rare cosmic accidents but relatively common occurrences. Each new discovery also helps refine our understanding of the habitable zone concept itself. The traditional definition focuses on the possibility of liquid water, but comparing different exoplanets has led to more nuanced models incorporating factors like planetary magnetic fields, atmospheric composition, and stellar activity. These expanded models help scientists better assess which discovered worlds might truly be capable of supporting life. The rich diversity of potentially habitable exoplanets discovered to date, from the nearby TRAPPIST-1 system to the more distant Kepler-452b, demonstrates that the universe offers many different environmental templates for potentially life-supporting worlds. Each new discovery adds another piece to our understanding of how common or rare conditions similar to those on Earth might be throughout the cosmos. The diversity of potentially habitable worlds we've discovered raises the tantalizing question that has driven much of our exploration of the cosmos. Could any of these planets harbor life? When scientists consider the possibility of life on Kepler-452b, they must work with a combination of what we know about life on Earth. the measured properties of this distant world, and educated speculation about how life might adapt to different planetary conditions. If life exists, or ever existed, on Kepler-452b, it would have evolved under conditions significantly different from those on Earth, despite the similarities between the two planets' orbits and host stars. The most obvious difference is the stronger gravity, with an estimated mass around 5 times that of Earth. The surface gravity would be roughly twice what we experience. This stronger gravitational pull would affect any organisms in fundamental ways. Living things on Kepler-452b would likely evolve more robust support structures. Plants might grow shorter and thicker to support themselves against the stronger pull of gravity. Animal-like organisms would probably develop stronger skeletons, more powerful muscles, and possibly shorter, stouter body types that distribute weight more efficiently. The energy cost of moving vertically, climbing trees or flying, for instance, would be significantly higher, potentially making such adaptations less common or requiring specialized evolutionary solutions. The planet's age offers another fascinating angle to consider. At around 6 billion years old, Kepler-452b has existed about 1.5 billion years longer than Earth. If life emerged there early in the planet's history, as it seems to have done on Earth, it would have had significantly more time to evolve and diversify. For comparison, 1.5 billion years ago on Earth, the most complex organisms were primarily single-celled, with multicellular life just beginning to emerge. The additional evolutionary time on Kepler-452b could potentially allow for more complex adaptations and possibly more diverse ecosystems than we see on Earth. Another factor that would shape potential life is the slightly higher energy input from its star. Kepler-452b receives about 10% more light than Earth, which could influence the efficiency and nature of photosynthesis or equivalent energy-capturing processes. Organisms might evolve pigments optimized for different wavelengths of light, or develop more efficient cooling mechanisms to deal with potentially warmer conditions. If the planet has a thicker atmosphere, as its stronger gravity suggests, this could modulate temperature extremes and create more uniform climatic conditions globally. The composition and chemistry of Kepler-452b would fundamentally determine what types of life could exist there. If the planet has a composition similar to Earth, with abundant carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, the elements most crucial for life as we know it, then biochemistry roughly similar to Earth's might develop. However, even subtle differences in elemental abundances or environmental conditions could lead to significantly different biochemical solutions. For instance, if Kepler-452b has more efficient geological recycling of carbon due to its presumably more active interior, the availability of carbon in different environments might differ from Earth patterns. Similarly, if ocean chemistry differs due to different dissolved minerals, marine organisms might evolve alternative biochemical pathways adapted to those specific conditions. The history of Kepler-452b's star would also influence potential life. As its star has gradually brightened over billions of years, any life would have had to adapt to slowly warming conditions. This might select for organisms with greater adaptability or drive evolutionary innovations to cope with changing environments. Long-term climate shifts could lead to waves of extinction and speciation, potentially creating complex evolutionary histories. If Kepler-452b has active plate tectonics, as seems likely given its larger size, this would create diverse habitats through mountain building, creating islands, opening and closing ocean basins, and recycling nutrients through the biosphere. The continuous renewal of surface environments through geological activity has been crucial for Earth's long-term habitability and biodiversity, and might play a similar role on Kepler-452b. Scientists also consider the possibility that life on Kepler-452b might have taken entirely different evolutionary paths than on Earth. While Earth's particular history led to the dominance of DNA/RNA-based life with carbon backbones, Other biochemical foundations are theoretically possible. Alternative solvents to water, different information-carrying molecules, or novel metabolic pathways might have evolved under Kepler-452b's specific conditions. The atmospheric composition would strongly influence what metabolic strategies might be viable. Earth's oxygen-rich atmosphere, the product of photosynthetic organisms, enables the energy-efficient process of aerobic respiration that powers most complex life here. If Kepler-452b developed photosynthetic life, its atmosphere might similarly contain oxygen. However, depending on the planet's history and the specific adaptations of its life forms, different atmospheric compositions could emerge, supporting entirely different metabolic systems. Any oceans on Kepler-452b would likely be crucibles for life, just as they were on Earth. The greater surface gravity might create shallower but more extensive ocean basins, potentially with stronger currents and wave action. Marine organisms would evolve accordingly, perhaps with more streamlined bodies or stronger anchoring mechanisms depending on their ecological niches. The day-night cycle, presumably similar to Earth's if the planet has a comparable rotation rate, would drive daily rhythms in any surface-dwelling organisms. However, if Kepler-452b rotates at a different rate, life would adapt to whatever cycle exists. Slower rotation might lead to organisms adapted to longer periods of light and dark, while faster rotation could create different patterns of activity and rest among living things. Even if Kepler-452b has all the right ingredients for life, there's no guarantee that life actually emerged there. The origin of life on Earth still holds many mysteries, and we don't know how probable the transition from chemistry to biology might be given favourable conditions. Kepler-452b could be a world with perfect conditions for life that nonetheless remains sterile simply due to chance or some overlooked factor. Conversely, the planet's longer existence within the habitable zone means that life has had more opportunities to emerge and more time to develop complexity once established. If the emergence of life follows predictable chemical pathways given the right conditions, then Kepler-452b's extended timeline improves the odds that such processes could have occurred. The planet's size puts it at the boundary where some exoplanets transition from rocky super-Earths to gaseous mini-Neptunes. If Kepler-452b does indeed have a substantial gaseous envelope rather than a solid surface, traditional surface life as we know it would be impossible. However, even in such scenarios, there might be layers within the atmosphere where temperatures and pressures could support floating organisms adapted to aerial life, though this stretches our understanding of potential adaptations. The question of whether life exists on Kepler-452b remains purely theoretical for now, as we lack the technological capability to detect biosignatures at such distances. Future telescopes might someday analyze the spectral fingerprint of its atmosphere, looking for chemical disequilibrium that could indicate biological processes. But even these observations would likely provide ambiguous results requiring careful interpretation. Despite these limitations, considering potential life scenarios on worlds like Kepler-452b helps scientists refine their understanding of the parameters for habitability and the possible variations life might take under different planetary conditions. Each new exoplanet discovery provides another test case for these evolving models of astrobiology and planetary habitability. While contemplating the possibility of life on Kepler-452b stirs the imagination, the prospect of humans ever visiting or colonizing this world faces obstacles so immense that they place such endeavors firmly in the realm of theoretical speculation rather than practical planning. The challenges begin with the most fundamental: distance. Kepler-452b lies approximately 1,400 light-years from Earth. This means that light itself, travelling at 300,000 kilometers per second, the fastest speed physically possible according to our understanding of physics, takes 1,400 years to make the journey. To put this in perspective, If we had sent a message at light speed during the fall of the Western Roman Empire, it would just be arriving at Kepler-452b now. Current human spacecraft technology falls drastically short of light speed. The fastest spacecraft we've built, such as the Parker Solar Probe, can reach speeds of about 700,000 kilometers per hour under ideal conditions. At such speeds, a journey to Kepler-452b would take millions of years, longer than humans have existed as a species. Even theoretical propulsion systems that might someday approach a small percentage of light speed would still require thousands of years to reach this distant world. The timescale involved means any mission would need to be multi-generational. Thousands of people would live entire lives aboard a spacecraft, never seeing either Earth or their destination, serving merely as links in a chain of generations. This raises profound questions about how to maintain a stable society, prevent technological regression, and preserve the mission's purpose across dozens or hundreds of generations. Resource requirements for such a journey would be equally staggering. A self-contained habitat supporting human life for millennia would need extraordinarily robust and redundant life support systems. The spacecraft would need to recycle virtually everything: water, period, air, organic materials, with near-perfect efficiency over timescales far longer than any human-made system has ever operated. Food production would require sustainable agricultural systems operating continuously for thousands of years. Energy generation would need to function reliably for the entire journey, likely requiring nuclear power sources with fuel reserves sufficient for millennia or advanced solar collection systems that could harvest enough energy in the dim regions between stars. The psychological challenges might prove even more daunting than the technical ones. Humans evolved in open environments with skies, horizons, and diverse ecosystems. Confining people to an artificial habitat for generations, no matter how well designed, would impose psychological stresses we barely understand. Each generation would know only the spacecraft as home, with Earth and Kepler-452b existing merely as abstract concepts or distant goals they would never personally experience. Maintaining genetic diversity would present another critical challenge. A founding population would need to be large enough to prevent harmful inbreeding effects over many generations. Scientists estimate that at minimum, several thousand genetically diverse individuals would be needed to maintain a healthy human population over such extended periods, significantly increasing the size and resource requirements of any generation ship. Even if these immense challenges of transit could somehow be overcome, the arrival at Kepler-452b would present an entirely new set of obstacles. The stronger gravity would immediately stress human physiology. Humans born and raised in Earth normal gravity already experience significant health problems when exposed to lower gravity, as seen in astronauts returning from extended space missions. The higher gravity of Kepler-452b would likely cause even more severe problems: compressed spines, strained hearts, and difficult breathing. Any humans born and raised during the journey in artificial Earth-like gravity would face immediate and potentially life-threatening challenges upon arrival. Adaptation to higher gravity might eventually occur over generations, but the transition period would be physically demanding and potentially dangerous. The atmospheric composition presents another unknown but critical factor. Even if Kepler-452b has an atmosphere containing oxygen, the precise mixture of gases would almost certainly differ from Earth's. Slightly too little oxygen would cause chronic altitude sickness-like symptoms. Too much could prove toxic. Other gases, present even in small quantities, might be harmful or fatal to humans, not evolved to filter or process them. Pathogens present a two-way concern. Any life on Kepler-452b might include microscopic organisms that could prove dangerous to humans who have no evolved immunity to them. Conversely, microbes brought from Earth could potentially devastate any native ecosystems through unintended contamination. While cross-species infection between truly alien biologies might be rare, the uncertainty itself represents a significant risk. Radiation exposure poses yet another hazard. If Kepler-452b has a weaker magnetic field than Earth or thinner atmospheric protection, surface radiation levels could be higher than humans can safely tolerate long term. Conversely, if the planet has a stronger magnetic field, as its larger size might suggest, this could provide better radiation protection than Earth offers. The practical challenges of establishing infrastructure on a world with different gravity, potentially different atmospheric pressure, and unknown surface conditions would require extensive adaptation of all our engineering knowledge. Buildings, vehicles, tools, and farming equipment designed for Earth conditions would need significant redesign to function properly under Kepler-452b's stronger gravitational pull. Beyond the physical and engineering challenges lie ethical considerations. If Kepler-452b harbours native life, human colonization could threaten these organisms through competition, predation, or contamination. The question of whether humans have the right to potentially disrupt or endanger another world's biosphere raises complex ethical issues that go beyond mere technical feasibility. The economics of such an enterprise are equally mind-boggling. The resources required to build a generation ship capable of making this journey would dwarf the largest projects in human history by orders of magnitude. The return on such an investment would be effectively zero for anyone involved in funding or building it, as no benefits would return to Earth for thousands of years, if ever. Despite these overwhelming challenges, theoretical discussions about interstellar colonization have value. They push the boundaries of our technological imagination, highlight the true scale of the universe we inhabit, and force us to confront the limitations of our current understanding of physics and biology. They also underscore the preciousness of Earth, our one confirmed habitable world, and the importance of preserving it. The vast distances to even the nearest potentially habitable exoplanets serve as a sobering reminder of our physical isolation in the cosmos. While we can study places like Kepler-452b remotely and learn much about them through increasingly sophisticated observations, actually visiting such worlds remains, for now, beyond our reach. This reality encourages us to focus on more accessible targets for human exploration, like our Moon and Mars, while continuing to study distant worlds like Kepler-452b through ever-improving telescopes and instruments. While the practical challenges of visiting Kepler-452b remain insurmountable with current or foreseeable technology, the discovery of this distant world has already made a journey of sorts, not through physical space, but through human culture. The announcement of Kepler-452b's discovery on July 23, 2015, captured public imagination in a way that few scientific discoveries do. Media outlets worldwide ran headlines proclaiming the discovery of Earth's cousin or older sibling, and the planet quickly entered popular consciousness in a manner that reveals much about how we as humans process and relate to scientific discoveries of this magnitude. The cultural impact of Kepler-452b began with how NASA itself framed the discovery. The space agency's press release described it as Earth's bigger dot, older cousin, immediately establishing a familial relationship that made the distant planet seem more relatable. This framing was picked up by news organizations globally, with headlines like NASA discovers Earth-like planet appearing on front pages and leading broadcasts. Major newspapers, television networks, online publications, and social media platforms amplified the story, turning a distant exoplanet into a household name overnight. What made this particular discovery resonate so deeply with the public? Several factors contributed to its cultural impact. First, the timing came after years of exoplanet discoveries that had gradually prepared the public for the idea of worlds beyond our solar system. Kepler-452b arrived at a moment when people were primed to appreciate its significance, but not yet saturated with similar discoveries. Second, the specific characteristics of the planet, orbiting in the habitable zone of a sun-like star with a year similar to Earth's, created strong parallels to our home world that were easy to communicate and understand. The visual representations of Kepler-452b also played a crucial role in its cultural impact. Since the planet is far too distant to photograph directly, NASA released artists' impressions showing a blue-green world with swirling clouds, continents, and oceans. These images, while clearly labelled as artistic concepts rather than actual observations, nonetheless created a concrete visual reference that helped people envision this distant world. The power of these visualizations to shape perception cannot be overstated. Many people now picture Kepler-452b as a lush, Earth-like planet, despite the fact that we have no direct information about its surface features or conditions. The discovery quickly permeated popular culture beyond the science pages. References to Kepler-452b appeared in television shows, movies, songs, and literature. Science fiction writers incorporated it into stories, sometimes imagining civilizations on this real but mysterious world. Video games used it as a setting for extraterrestrial adventures. Its name became shorthand for discussing humanity's potential future homes beyond Earth, appearing in discussions about space colonization and the long-term future of our species. For many people, Kepler-452b transformed abstract discussions about exoplanets into something more tangible. Before this discovery, exoplanets were primarily mathematical constructs, data points with orbital periods and mass estimates. Kepler-452b, with its Earth-like orbit around a Sun-like star, provided a mental hook that made exoplanets feel like real places rather than just astronomical statistics. People began to wonder not just about the physics of this world, but what it might be like to stand on its surface, to experience its stronger gravity, to see its landscapes. Educational institutions quickly incorporated Kepler-452b into their curricula. The planet became a teaching tool in classrooms from elementary schools through universities, used to illustrate concepts in astronomy, planetary science, and astrobiology. Students who might have found it difficult to engage with abstract astronomical concepts could now focus their curiosity on a specific world with properties they could relate to and compare with Earth. The discovery also influenced how people think about humanity's place in the cosmos. For centuries, the Earth was considered unique, the only known world capable of supporting life as we know it. The discovery of Kepler-452b and other potentially habitable exoplanets has gradually shifted this perception, suggesting that Earth-like conditions might be relatively common throughout our galaxy. This realization has both humbled and inspired, suggesting that our planet, while special to us, may be one of many worlds with conditions amenable to life. Religious and philosophical discussions incorporated Kepler-452b as well. Many religious leaders and scholars found ways to integrate the possibility of other habitable worlds into their theological frameworks. For some spiritual traditions, the discovery reinforced the magnitude and diversity of creation. For others, it prompted reconsideration of doctrines developed when Earth was thought to be the only inhabited world. Philosophical discussions about the meaning of humanity's place in the universe gained new dimensions as people contemplated the implications of potentially habitable worlds scattered throughout the galaxy. The naming of Kepler-452b itself reflects cultural conventions rather than any intrinsic property of the planet. The name combines the telescope that discovered it, Kepler, the catalogue number of its star, 452, and a letter designation indicating it's the first planet discovered in the system, B. This technical designation lacks the mythological richness of planets in our solar system like Mars or Venus, yet it has become familiar through repetition in scientific and popular contexts. Some science communicators and space enthusiasts have suggested more evocative nicknames, but the technical designation remains its official name. Perhaps most significantly, Kepler-452b has become a symbol that concentrates broader hopes, fears, and curiosities about space exploration and the search for life beyond Earth. It serves as a focal point for discussions about humanity's future. the potential for other life-bearing worlds, and our long-term destiny as a species. Despite the fact that no human will visit this world in the foreseeable future, it has become a cultural touchstone, a concrete example that helps frame abstract discussions about cosmic habitability. The cultural impact of Kepler-452b demonstrates how scientific discoveries can transcend their technical details to become part of our shared imagination. From news reports and educational materials to creative works and philosophical discussions, this distant world has influenced how we think about our place in the universe. Even as astronomers continue to discover more exoplanets, some with characteristics that might make them even better candidates for habitability, Kepler-452b retains its special place in public consciousness as one of the first exoplanets to be widely recognized as a potentially Earth-like world. The widespread cultural resonance of Kepler-452b has helped generate public support for the astronomical research that makes such discoveries possible. Funding for space telescopes, observatories, and research programs often depends partly on public interest and appreciation. By capturing imagination and making abstract astronomical research feel relevant and exciting, discoveries like Kepler-452b help sustain the scientific enterprise that continues to expand our understanding of the cosmos. The cultural significance of Kepler-452b connects directly to one of the most profound scientific questions humans have ever asked. Are we alone in the universe? This question bridges our discussion to the field of astrobiology, which studies the origin, evolution, and distribution of life throughout the cosmos. When astrobiologists examine worlds like Kepler-452b, they're looking for environments that could potentially support the complex chemistry of life as we know it. Astrobiology approaches the question of extraterrestrial life through multiple scientific disciplines, combining astronomy, biology, chemistry, geology, atmospheric science, and oceanography. This interdisciplinary approach reflects the complex interplay of factors that contribute to planetary habitability. When assessing a world like Kepler-452b, astrobiologists consider a range of conditions beyond just its location in the habitable zone. The most fundamental requirement for life as we know it is liquid water, which serves as the solvent in which biochemical reactions occur. Water has unique properties that make it particularly suited for this role. It dissolves many compounds, facilitates chemical reactions, transports nutrients, and helps regulate temperature. While scientists remain open to the possibility of life based on other solvents, water represents our primary reference point when evaluating habitability. Beyond water, life requires an energy source to drive metabolic processes. On Earth, most life ultimately depends on sunlight captured through photosynthesis, though some ecosystems near deep-sea hydrothermal vents rely on chemical energy from the planet's interior. A potentially habitable exoplanet would need available energy sources, whether stellar radiation like Kepler-452b receives from its sun, or alternative sources like tidal heating or chemical gradients. Chemical building blocks represent another essential requirement. Life on Earth is based primarily on 6 elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, sometimes abbreviated as CHNOPS. These elements must be available in usable forms for life to develop and sustain itself. Carbon is particularly important because of its unparalleled ability to form complex, stable molecules with diverse structures and functions. While theoretically other elements like silicon could form the backbone of alternative biochemistries, carbon's versatility makes it the leading candidate for life anywhere. Environmental stability over long timescales also plays a crucial role in habitability assessments. Life takes time to emerge and evolve on Earth. Simple life appeared relatively early, but complex multicellular organisms required billions of years to develop. A planet that experiences extreme temperature fluctuations, rapidly changing atmospheric conditions, or frequent sterilizing events would face challenges sustaining complex life. Kepler-452b's long residence in its star's habitable zone suggests it might have maintained relatively stable conditions over billions of years, providing the time needed for potential biological evolution. Protection from harmful radiation represents another important factor. Earth's magnetic field and atmosphere shield surface life from cosmic rays and stellar radiation that can damage biological molecules. Without such protection, maintaining complex surface life becomes significantly more challenging. While we don't know if Kepler-452b has a magnetic field, its larger size suggests it might generate a stronger one than Earth's, potentially providing enhanced radiation protection. The cycling of elements through a planet's geological, atmospheric, and potentially biological systems, known as biogeochemical cycles, also contributes to long-term habitability. On Earth, processes like weathering, volcanic activity, and plate tectonics help regulate atmospheric composition over long timescales. A potentially habitable exoplanet would likely need similar feedback mechanisms to maintain conditions suitable for life, despite changes like its star's increasing luminosity over time. Astrobiologists also consider more speculative factors when assessing habitability. For instance, some research suggests that Jupiter's gravitational influence helped shield Earth from excessive comet and asteroid impacts. Similarly, Earth's large moon stabilizes our planet's axial tilt, preventing extreme seasonal variations that could challenge life. The presence or absence of such factors in exoplanetary systems might influence their long-term habitability in ways we're still working to understand. When applying these criteria to Kepler-452b, astrobiologists face significant uncertainties due to the limited data available. The planet's position in the habitable zone and its possibly rocky composition represent positive indicators. But questions remain about its atmosphere, surface conditions, and many other factors. Future observations might provide some answers, but a comprehensive assessment of Kepler-452b's habitability will likely remain beyond our reach for decades. The search for biosignatures, observable evidence of life, represents the next frontier in exoplanet research. These might include atmospheric gases like oxygen and methane existing together in disequilibrium, which on Earth results from biological activity, surface reflectance patterns suggestive of vegetation, or even technological signatures that could indicate intelligent life. Detecting such biosignatures on distant exoplanets requires extremely sensitive observations that push the limits of current technology. Though next-generation telescopes may begin to provide some insights, astrobiologists remain careful not to equate habitability with inhabited status. A planet can have all the right conditions for life without life actually emerging there. The origin of life itself remains one of science's great mysteries. We don't yet understand exactly how chemistry transitioned to biology on Earth, making it difficult to assess how likely this transition might be elsewhere. Some scientists argue it may be relatively common given suitable conditions, while others suggest it might require rare circumstances or a series of unlikely events. The study of extreme environments on Earth has expanded our understanding of the potential range of conditions that might support life. Organisms have been discovered thriving in acidic hot springs, deep underground, in Antarctic ice, and in highly saline or radiation-filled environments once thought incompatible with life. These extremophiles have pushed the boundaries of what we consider habitable conditions, suggesting that life might adapt to a broader range of environments than previously thought. Laboratory experiments in synthetic biology and origin of life research complement astronomical observations by helping us understand how life might begin and function under different conditions. Scientists have created artificial cells, synthesized alternative genetic molecules, and explored chemical reactions that might have led to the first self-replicating systems. This research helps expand our conception of what might be possible on worlds like Kepler-452b, while keeping our expectations grounded in chemical and physical reality. The field of astrobiology has evolved significantly since its emergence as a distinct discipline in the late 20th century. Early approaches often relied heavily on Earth analogies, asking simply whether a planet was Earth-like. Modern astrobiology takes a more nuanced approach, recognizing that habitability exists along a spectrum rather than as a binary condition, and that life might adapt to environments quite different from those found on Earth. This evolving perspective shapes how scientists evaluate the potential habitability of worlds like Kepler-452b. As we continue to discover more exoplanets and develop more powerful tools to study them, our understanding of habitability and the potential for extraterrestrial life will continue to evolve. Kepler-452b represents just one data point in this ongoing investigation, a particularly interesting one given its similarities to Earth, but still just one world among billions in our galaxy alone. The quest to understand whether we share our universe with other forms of life continues to drive astronomical research and capture the human imagination across cultural boundaries. The astrobiological assessment of potentially habitable worlds like Kepler-452b naturally leads us to consider how such planets form and evolve over billions of years. Unlike planets in our own solar system, which we've studied up close with spacecraft and can analyse directly, our understanding of Kepler-452b's formation history must be constructed through modelling, theoretical work, and extrapolation from what we know about planetary formation in general. Kepler-452b likely began its journey approximately 6 billion years ago, when its star system was nothing more than a rotating cloud of gas and dust. As this nebular material collapsed under its own gravity, most of it concentrated in the centre to form the young star Kepler-452, while the remaining material flattened into a spinning protoplanetary disk. Within this disk, tiny dust particles began sticking together through electrostatic forces, gradually forming pebbles, then rocks, and eventually planetesimals, bodies large enough for their own gravity to play a significant role in their continued growth. The region where Kepler-452b formed, at roughly 1 astronomical unit from its star, would have been a zone where rocky materials could condense in the early solar system. Closer to the star, temperatures would have been too high for anything but metals and certain minerals to remain solid. Further out, beyond what astronomers call the snow line, water ice and more volatile compounds could condense, leading to more gas-rich planet formation. Kepler-452b's position suggests it initially formed primarily from rocky materials, similar to Earth's formation process. As these early planetesimals grew through continued collisions and accretion of smaller bodies, the young Kepler-452b would have entered a phase known as oligarchic growth, where a relatively small number of planet-sized bodies dominated their orbital regions, sweeping up remaining material. This phase is typically marked by giant impacts between protoplanetary bodies, including potentially cataclysmic collisions that could reshape a forming planet's composition or orientation. The planet's larger size compared to Earth might result from several possible formation scenarios. It may have formed in a region of the protoplanetary disk with higher density of building materials, allowing it to accrete more mass. Alternatively, the architecture of the early Kepler-452 system might have directed more planetesimals toward this orbital region, enhancing its growth. The planet might also have experienced fewer giant impact events that could have stripped away material, allowing it to retain more of its original mass. Being a more massive planet, Kepler-452b would have generated more internal heat during its formation, both from the energy of accretion and from the decay of radioactive elements incorporated into its structure. This greater heat production would have significant consequences for its early evolution, potentially leading to more extensive melting of its interior, more thorough differentiation into core, mantle, and crust, and possibly more vigorous volcanic activity on its young surface. The early Kepler-452b likely experienced a phase called the Late Heavy Bombardment, similar to what occurred in our solar system, when numerous asteroids and comets impacted the forming planets. For Kepler-452b, with its stronger gravitational pull, this bombardment might have been even more intense, as its gravity would attract more impactors from surrounding space. These impacts would have delivered additional materials to the young planet, potentially including significant quantities of water and organic compounds, key ingredients for potential habitability. Water delivery is particularly important in planetary formation history. Earth is thought to have received much of its water from asteroids and comets that formed beyond the snow line and were later directed inward toward the terrestrial planets. A similar process likely occurred in the Kepler-452 system. The planet's stronger gravity would help it retain this delivered water against loss to space, potentially resulting in a world with more extensive surface water than Earth, depending on the specific impact history and the planet's initial composition. The geological evolution of Kepler-452b over its 6 billion year history would be influenced significantly by its larger mass. More massive planets tend to retain more internal heat for longer periods, which can drive more vigorous and longer-lasting geological activity. If Kepler-452b has plate tectonics similar to Earth's, the movement of crustal plates might occur at different rates or with different patterns due to the thicker crust that would likely form under higher gravity conditions. Volcanic activity on Kepler-452b could have been more extensive throughout its history than on Earth, driven by its greater internal heat. This volcanism would play a crucial role in cycling materials between the planet's interior and surface, potentially creating a more robust carbon cycle that could help regulate atmospheric composition over long timescales. More vigorous volcanism might also create more dramatic surface features, though the higher gravity would tend to flatten topographic relief compared to Earth. As Kepler-452b evolved over billions of years, its star was also changing. Like our Sun, Kepler-452 has gradually increased in luminosity over its lifetime. When the star was younger, about 4.5 billion years ago, it would have been approximately 10% less luminous than it is today. This means Kepler-452b would have received less stellar energy in its youth than it does now, potentially making it cooler in its early history, despite being in what we now consider the habitable zone. This changing stellar output creates what planetary scientists call the faint young sun paradox. For both Earth and Kepler-452b, the reduced energy from their younger stars might have made both planets too cold for liquid water early in their histories. Yet geological evidence on Earth suggests water has been present for at least 3.8 billion years. The solution likely involves different atmospheric composition in the planet's early histories, with higher concentrations of greenhouse gases like carbon dioxide and methane trapping more heat despite the lower solar input. For Kepler-452b, this balance between changing stellar output and atmospheric composition would play out over billions of years as its star brightened. Feedback mechanisms involving the carbon cycle, weathering of rocks, and potentially biological processes if life emerged, would need to gradually reduce atmospheric greenhouse gases to prevent overheating. The planet's position slightly further from its star than Earth is from the Sun might have helped buffer these changes, providing more margin for adaptation to the increasing stellar luminosity. Another crucial aspect of Kepler-452b's evolution would be the development and maintenance of its magnetic field. Terrestrial planets generate magnetic fields through the motion of electrically conductive fluid in their cores, primarily liquid iron in Earth's case. Kepler-452b's larger mass suggests it might generate a stronger magnetic field than Earth's, which would provide better protection against stellar radiation and help prevent atmospheric stripping by stellar winds. This enhanced protection could be significant for long-term habitability, especially as its star aged and potentially became more active. The combined story of Kepler-452b's formation and evolution illustrates the complex interplay of factors that shape a planet's development over billions of years. From its birth in a swirling protoplanetary disk to its current state as a mature planet orbiting an aging star, each stage of its history involves processes operating across vast timescales that collectively determine its potential habitability. While many details of this history remain speculative given our limited observational data, the theoretical framework of planetary science allows us to construct a plausible narrative for how this distant world came to be. Understanding the formation and evolution of planets like Kepler-452b does more than satisfy scientific curiosity. It fundamentally reshapes our perspective on humanity's place in the cosmos. The discovery of this distant world, along with thousands of other exoplanets, has profound implications that extend beyond astronomy into how we understand ourselves and our relationship to the universe. When Copernicus proposed in the 16th century that Earth orbits the Sun rather than vice versa, it triggered what historians call the Copernican Revolution, a fundamental shift in how humans perceived their place in the cosmos. No longer at the literal centre of creation, Earth became just one planet among several. The discovery of Kepler-452b and other potentially habitable exoplanets represents a second Copernican revolution of sorts. Not only is Earth not at the centre of the physical universe, but it may not even be unique in its capacity to support complex life. This realization has rippled through human thought in ways both subtle and profound. For millennia, many human belief systems positioned Earth as a special creation, uniquely designed to support life. The existence of a planet like Kepler-452b orbiting in the habitable zone of a Sun-like star, potentially rocky, and of a size that could support an atmosphere, suggests that the conditions we once thought made Earth exceptional might be relatively common throughout our galaxy. Statistical analyses of exoplanet discoveries indicate there could be billions of potentially habitable planets in our galaxy alone. If we extrapolate from the frequency of exoplanets detected around surveyed stars, as many as 1 in 5 Sun-like stars might host an Earth-sized planet in its habitable zone, with hundreds of billions of stars in the Milky Way. This suggests an almost inconceivable abundance of potentially life-supporting worlds. The implications of this abundance challenge us to reconsider long-held assumptions. If potentially habitable planets are common, why haven't we detected signs of extraterrestrial civilizations? This question, formalized as the Fermi paradox, becomes more pressing with each new potentially habitable world we discover. The silence from the cosmos, despite the apparent multitude of potential homes for life, forces us to confront the possibility that either the emergence of life is rarer than we think, the development of intelligence and technology is an unusual outcome, or there are natural barriers that prevent interstellar communication or travel. Various religious traditions have begun integrating these discoveries into their theological frameworks. Many religious thinkers argue that their traditions are expansive enough to accommodate the possibility of life beyond Earth. Some point out that nothing in their sacred texts explicitly states that Earth is the only inhabited world, while others suggest that divine creation could certainly extend beyond our planet. Still others propose that discovering life elsewhere would simply reveal another aspect of creation previously unknown to us. The existence of worlds like Kepler-452b also influences how we think about humanity's long-term future. If Earth is just one of many potentially habitable planets, the long-term survival of consciousness, intelligence, and even human values need not be tied exclusively to our home planet's fate. While practical interstellar travel remains far beyond our current capabilities, the knowledge that other potentially habitable worlds exist provides a psychological framework for imagining humanity's expansion beyond Earth, even if such expansion lies centuries or millennia in the future. These discoveries also affect how we value Earth itself, far from diminishing our home planet's importance to us. Finding other potentially habitable worlds often heightens appreciation for Earth's known habitability. While planets like Kepler-452b might have conditions that could support life, Earth is the one planet we know with certainty does support a rich biosphere including intelligent life. This known habitability, contrasted with the merely potential habitability of distant exoplanets, underscores Earth's immediate importance to humanity and all terrestrial life. The vast distances involved in these discoveries, Kepler-452b lies 1,400 light-years away, also highlight the physical limitations that constrain human exploration. Even communicating with any potential inhabitants of such a world would involve a 2,800-year round trip for signals travelling at light speed. These immense distances create a cosmic horizon of sorts, where direct interaction becomes impractical across human timescales. This reality forces us to confront the limitations of direct knowledge acquisition and the vast scales of time and space that characterize our universe. These discoveries also influence how we conceptualize alien life. Rather than the fantastic creatures of science fiction, astrobiologists now discuss potential extraterrestrial life in terms of comparative planetary environments, biochemistry, and evolutionary trajectories. Kepler-452b, with its similar orbit around a Sun-like star but larger size and stronger gravity, prompts scientists to consider how familiar life processes might adapt to slightly different planetary conditions. This represents a more nuanced approach to extraterrestrial life, grounded in comparative planetary science rather than pure speculation. The search for and discovery of exoplanets has also influenced how humanity prioritizes scientific research and technology development. Major space agencies and research institutions have committed substantial resources to developing technologies specifically designed to detect and characterize potentially habitable exoplanets. These investments represent a collective decision that understanding our cosmic context and the potential for life beyond Earth deserves significant scientific attention, reflecting a shared human curiosity about our place in the universe. Perhaps most fundamentally, discoveries like Kepler-452b challenge us to expand our cosmic perspective. Throughout most of human history, the world referred exclusively to Earth, our immediate physical environment. The scientific advances of recent centuries have progressively expanded this perspective to include our solar system, our galaxy, and beyond. Exoplanet discoveries push this expansion further by identifying specific other worlds that might, in some ways, be similar to our own. Rather than an abstract awareness that other planets exist, we now have concrete examples with known properties that we can compare to Earth. This expanded perspective doesn't diminish humanity's importance, but rather contextualizes it within a larger cosmic picture. We now understand that we inhabit one planet among many, orbiting one star among billions, in one galaxy among trillions. Yet, paradoxically, this cosmic perspective also highlights the apparent rarity of consciousness and the ability to comprehend these scales. Even if life exists elsewhere, our capacity to discover planets like Kepler-452b and contemplate their significance represents something possibly quite special in the universe. The ongoing discovery of potentially habitable worlds continues to shape human thought in ways both practical and profound. From influencing research priorities and space exploration goals to challenging long-held philosophical and religious concepts, planets like Kepler-452b have become integrated into how we understand ourselves and our place in the cosmos. As our observational capabilities improve and we learn more about these distant worlds, their influence on human thought and culture will likely continue to evolve, building upon the foundation that exoplanet discoveries have already established. The philosophical implications of discovering worlds like Kepler-452b naturally raise questions about what we might learn about this distant planet in the future. While current observations provide tantalizing hints about its nature, our view remains limited by the technologies available today. Looking ahead, a remarkable array of new telescopes and observational technologies are being developed that promise to dramatically enhance our understanding of this and other potentially habitable exoplanets. The James Webb Space Telescope, launched in December 2021, represents the most significant near-term advance in our ability to study distant worlds like Kepler-452b. As the successor to the Hubble Space Telescope, Webb operates primarily in the infrared portion of the spectrum, which is ideal for studying exoplanets. The telescope's large 6.5-metre primary mirror collects significantly more light than previous space telescopes, allowing it to detect fainter signals from distant planetary systems. One of Webb's most powerful capabilities is its ability to perform transit spectroscopy, analysing the tiny fraction of starlight that filters through a planet's atmosphere during a transit. As this light passes through the atmosphere, certain wavelengths are absorbed by different gases, creating a spectral fingerprint that can reveal atmospheric composition. For a planet like Kepler-452b, Webb might potentially detect the presence of water vapour, carbon dioxide, methane, or even potential biosignatures like oxygen if they exist in sufficient quantities. However, studying Kepler-452b specifically presents significant challenges even for Webb. The planet's host star is relatively faint, about 20th magnitude, and the signal from the planet's atmosphere would be extraordinarily small compared to the star's light. Additionally, the planet's long orbital period of 385 days means transit opportunities are rare, giving astronomers few chances to collect data. While Webb will certainly advance our understanding of exoplanets as a category, Kepler-452b itself might remain a challenging target even for this powerful observatory. On the ground, a new generation of extremely large telescopes is under construction that will revolutionize our ability to study distant worlds. Three major projects stand out. The 30-metre telescope planned for Mauna Kea in Hawaii, the European Extremely Large Telescope, ELT, being built in Chile's Atacama Desert, and the giant Magellan Telescope, also under construction in Chile. With primary mirrors measuring 30 metres, 39 metres, and 25 metres respectively, these observatories will collect unprecedented amounts of light, allowing for more detailed studies of faint objects like Kepler-452b and its star. These giant telescopes will employ advanced adaptive optics systems that compensate for the blurring effects of Earth's atmosphere, allowing them to achieve resolution approaching that of space telescopes. They will also use sophisticated spectrographs capable of detecting minute spectral features that could reveal details about exoplanet atmospheres. For Kepler-452b, these capabilities might allow astronomers to better characterize its host star, potentially detecting the tiny wobble caused by the planet's gravitational pull and thus determining its mass more accurately. Looking further ahead, NASA and other space agencies are developing dedicated exoplanet observatories that could provide even more detailed views of worlds like Kepler-452b. Concepts under consideration include missions like the Large UV/Optical/IR Surveyor (LUVOIR) and the Habitable Worlds Observatory, which would use advanced coronagraphs or star shades to block out the overwhelming light of host stars, potentially allowing direct imaging of planets in their habitable zones. Direct imaging represents a particularly exciting frontier in exoplanet science. Rather than merely detecting a planet's transit or its gravitational effect on its star, direct imaging would capture actual photons of light from the planet itself, either reflected from its star or emitted as thermal radiation. This would provide information about surface features, cloud patterns, and possibly even evidence of oceans or continents. For a distant world like Kepler-452b, such imaging would require extraordinary technological advances, including telescopes with mirrors potentially hundreds of meters across or interferometric arrays of multiple telescopes working together to achieve the necessary resolution. Space-based interferometry offers another promising approach for future observations. By flying multiple telescopes in precise formation and combining their light, astronomers can achieve resolution equivalent to a much larger telescope. Concepts like NASA's previously proposed Terrestrial Planet Finder or ESA's Darwin mission envisioned arrays of spacecraft working together to study exoplanet atmospheres in unprecedented detail. While funding constraints have delayed these specific missions, the underlying technology continues to develop and could eventually provide our most detailed views of worlds like Kepler-452b. advances in data analysis techniques will complement these new observational technologies. Machine learning algorithms are increasingly being applied to astronomical data, helping to extract faint signals from noisy backgrounds and identify patterns that might be missed by traditional analysis methods. For exoplanet research, these computational approaches could help astronomers identify subtle atmospheric signatures in transit data or detect periodic variations in light that might indicate weather patterns, rotation, dot, or even artificial structures on distant worlds. The timeline for these advances varies considerably. Webb is already operational and beginning its scientific observations, while the ground-based extremely large telescopes are expected to see first light in the late 2020s. More ambitious concepts like large space-based interferometers might not be realized until the 2040s or beyond. Each advance will incrementally improve our understanding of Kepler-452b and similar worlds, gradually filling in the picture of these distant planets and their potential habitability. These technological developments reflect a sustained commitment to understanding exoplanets as a central goal of modern astronomy. From the Kepler mission that discovered Kepler-452b to the next generation of observatories, significant resources are being directed toward answering fundamental questions about planetary systems beyond our own. This investment recognizes that understanding the prevalence and nature of potentially habitable worlds addresses one of humanity's most profound questions: whether we are alone in the universe. The challenges of observing Kepler-452b and similar worlds also drive innovation across multiple fields. Developing the technologies needed to detect and characterize these distant planets requires advances in optics, detector technology, spacecraft design, computing, and numerous other disciplines. These advances often find applications beyond astronomy, contributing to broader technological progress in areas ranging from medical imaging to remote sensing. As our observational capabilities improve, Kepler-452b will gradually transform from a distant data point with a few known parameters to a world we can characterize in increasing detail. While we may never observe it with the clarity we can achieve for planets in our own solar system, each technological advance brings us closer to understanding this tantalizing world that shares key characteristics with our own Earth. The improved ability to observe and characterize planets like Kepler-452b directly connects to one of the most profound questions humans have ever asked. Are we alone in the universe? This question has driven much of our exploration of space, and Kepler-452b plays a particularly interesting role in the search for extraterrestrial intelligence, SETI. Since the early 1960s, scientists have been using radio telescopes to search for artificial signals from beyond Earth. The discovery of potentially habitable exoplanets like Kepler-452b has given these searches specific targets, focusing on star systems where conditions might support technological civilizations. Rather than scanning the entire sky, SETI researchers can prioritize their limited observing time on the most promising systems, with Kepler-452b and its star ranking high on that list. Several major radio astronomy facilities have conducted targeted observations of the Kepler-452 system, including the Allen Telescope Array in California, the Green Bank Telescope in West Virginia, and the Parkes Radio Telescope in Australia. These observations search across a range of radio frequencies, looking for narrow-band signals that would stand out from natural cosmic radio emissions and potentially indicate artificial origin. So far, no convincing evidence of artificial signals from the Kepler-452 system has been detected, but the search continues with increasingly sophisticated equipment and analysis techniques. What makes Kepler-452b particularly interesting for SETI research is the combination of its potentially Earth-like conditions and its greater age. At approximately 6 billion years old, the planet has existed about 1.5 billion years longer than Earth. If life emerged there on timescales similar to Earth, it would have had significantly more time to develop and potentially evolve intelligence. For comparison, Complex multicellular life on Earth only became abundant in the last 500 million years, and human civilization has existed for only a few thousand years. The additional evolutionary time available on Kepler-452b makes it an especially intriguing target in the search for advanced civilizations. Beyond traditional radio SETI, astronomers have begun searching for other potential technosignatures, observable evidence of technology that might indicate the presence of an intelligent civilization. These include optical laser pulses, which could be used for communication or propulsion systems, atmospheric pollutants that might indicate industrial activity, unusual infrared emissions that could suggest large-scale energy use, or even megastructures that might partially block starlight in unusual patterns. The Breakthrough Listen project, funded with $100 million by Russian-Israeli tech entrepreneur Yuri Milner, represents the most comprehensive SETI effort to date and has included Kepler-452b among its target systems. Using some of the world's most powerful radio telescopes, Breakthrough Listen is surveying the million closest stars to Earth and the centers of 100 galaxies, scanning billions of radio channels for potential artificial signals. This project has already collected more data than all previous SETI programs combined and continues to refine its search techniques. However, even if a technological civilization exists in the Kepler-452 system, detecting it presents enormous challenges. The vast distance, 1,400 light-years, means that any signals we detect would have been sent 1,400 years ago, and any response we might send wouldn't arrive until another 1,400 years had passed. This communications delay makes any form of conversation impossible on human timescales. Additionally, unless a civilization were deliberately transmitting powerful signals in our direction, their everyday communications might be too faint for us to detect at such distances. These practical limitations haven't deterred SETI researchers, who recognize that discovering any evidence of extraterrestrial intelligence would be one of the most profound scientific discoveries in human history, even if direct communication proved impossible. The mere knowledge that another technological civilization exists or existed would fundamentally transform our understanding of life's prevalence and evolution in the universe. Some SETI researchers have proposed that older star systems like Kepler-452 might be home to very advanced civilizations, potentially millions or billions of years ahead of our own technological development. Such civilizations might have capabilities far beyond our current understanding, potentially including extensive modification of their environments or even their stellar system. This has led to searches for more exotic technosignatures, such as unusual stellar properties or unexpected chemical compositions that might indicate advanced technological intervention. The concept of a technosignature, as distinct from a biosignature, has gained increasing scientific legitimacy in recent years. While biosignatures would indicate the presence of any life, technosignatures specifically point to intelligent life that has developed technology capable of modifying its environment in detectable ways. As our own civilization demonstrates, technology can create changes visible across interstellar distances, from radio broadcasts to atmospheric changes to nighttime illumination, potentially making technological activity easier to detect than life itself. Future telescopes will significantly enhance our ability to search for both biosignatures and technosignatures in the Kepler-452 system. The James Webb Space Telescope could potentially detect industrial pollutants in the planet's atmosphere if they exist in sufficient quantities. Similarly, extremely large ground-based telescopes might eventually be able to detect artificial lighting on the planet's night side or unusual atmospheric compositions that could indicate technological activity. The search for intelligence in systems like Kepler-452 also includes efforts to actively message these distant worlds, an approach known as Messaging Extraterrestrial Intelligence, METI. Some scientists and organizations have already sent deliberate radio transmissions toward promising star systems. though Kepler-452's great distance makes it a less practical target for such efforts compared to closer stars. These METI activities remain controversial, with some scientists arguing that announcing our presence to unknown civilizations carries potential risks that haven't been adequately considered. Despite decades of searching, SETI has not yet detected convincing evidence of extraterrestrial intelligence, leading to what's known as the Great Silence, or, more formally, the Fermi paradox. If habitable planets like Kepler-452b are relatively common, where are all the aliens? This apparent contradiction between the estimated abundance of suitable habitats for life and the lack of observable evidence for extraterrestrial civilizations has generated numerous proposed explanations. From the possibility that technological civilizations typically destroy themselves shortly after developing advanced technology, to the idea that intelligent life might be common but choose to remain undetectable for reasons we don't yet understand. The continued discovery of potentially habitable exoplanets like Kepler-452b both deepens this paradox and provides new opportunities to resolve it. Each new world we find that could potentially support life adds to the statistical puzzle of why we haven't detected other civilizations. At the same time, each new discovery gives SETI researchers another specific target to study, increasing the chances that we might eventually detect something if technological civilizations do exist beyond Earth. As our technological capabilities continue to advance, Kepler-452b will remain an important target in humanity's search for cosmic companions. While the vast distances involved make this search challenging, the scientific and philosophical significance of potentially discovering another technological civilization ensures that we will continue looking toward this distant world, listening for whispers of intelligence across the light years that separate us. The search for intelligent life on worlds like Kepler-452b leads us to consider what physical conditions might exist on such a planet, specifically its geological characteristics and the processes that might shape its surface and interior. While we cannot directly observe Kepler-452b's geology, planetary scientists can develop well-informed models based on the planet's known properties, principles of physics and geology, and our understanding of how larger rocky planets should behave. As a super-Earth with approximately 5 times Earth's mass and 1.6 times its diameter, Kepler-452b would experience significantly different geological processes than our home planet. The most fundamental difference stems from its stronger gravitational field, approximately twice what we experience on Earth. This increased gravity would influence virtually every aspect of the planet's geological development and ongoing processes. Starting at the planet's core, planetary scientists expect Kepler-452b would have differentiated into layers similar to Earth's structure, with a metallic core surrounded by a rocky mantle and a relatively thin crust. The increased mass would create greater pressures throughout the planet's interior. These higher pressures could cause minerals to form different crystal structures than they do on Earth, potentially creating exotic high-pressure phases not found naturally on our planet. The core of Kepler-452b likely consists primarily of iron and nickel, similar to Earth's core, but its greater size would allow it to retain more internal heat from both its formation and from radioactive decay of elements like uranium, thorium, and potassium. This additional heat would likely keep more of the core in a molten state for longer in the planet's history, potentially generating a stronger magnetic field than Earth's. A robust magnetic field would be crucial for protecting any potential atmosphere from being stripped away by stellar winds, particularly important given that Kepler-452, being an older star than our Sun, might produce more intense stellar activity. Moving outward to the mantle, the greater internal heat of Kepler-452b would drive more vigorous convection, the slow churning of semi-solid rock that ultimately powers plate tectonics on Earth. Whether the planet would actually have plate tectonics similar to Earth's remains an open question in planetary science. Some models suggest that planets significantly larger than Earth might develop a single-plate stagnant lid regime rather than mobile plates. as the increased gravity makes it harder to break and move large sections of crust. Others indicate that the increased internal heat could overcome this resistance, potentially resulting in more numerous, smaller plates moving more quickly than those on Earth. If Kepler-452b does have plate tectonics, the process would recycle surface materials into the interior and bring fresh material to the surface, creating a long-term carbon cycle crucial for climate regulation. The subduction of carbon-containing rocks followed by volcanic outgassing of carbon dioxide provides a thermostat-like mechanism on Earth that has helped maintain habitable conditions despite our Sun's increasing luminosity over billions of years. On Kepler-452b, this cycle might operate more efficiently due to more vigorous internal activity, potentially helping the planet remain habitable despite its star's greater age and luminosity. Volcanic activity on Kepler-452b would likely be more extensive and possibly more energetic than on Earth, driven by the planet's greater internal heat. Eruptions might be more frequent but potentially less explosive on average due to the stronger gravitational field, which would make it harder for gases to expand explosively as magma reaches the surface. The stronger gravity would also cause lava flows to spread more thinly and widely compared to similar eruptions on Earth. Over time, this volcanism would build features like shield volcanoes, though they might be broader and flatter than their earthly counterparts due to the stronger gravity. Mountain ranges on Kepler-452b would differ significantly from those on Earth, while tectonic processes might still create mountain ranges where plates collide. The stronger gravity would limit their maximum height. Mountains would tend to spread out laterally under their own weight rather than rising as high as they might on Earth. For comparison, Mars, with its weaker gravity, can support much taller mountains relative to its size than Earth can. Olympus Mons rises nearly 22 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. On Kepler-452b, the reverse would be true, with mountains likely reaching no more than half the relative height of Earth's tallest peaks. Erosion processes would also operate differently under higher gravity. Rivers would flow with greater force for a given slope, potentially carving wider, shallower valleys than those on Earth. Landslides and other mass-wasting processes would occur more readily as the stronger gravity more easily overcomes the internal strength of rocks. Weathering might proceed more quickly as the increased weight of overlying materials puts greater stress on underlying rocks, opening more fractures for water, roots, or other weathering agents to penetrate. The planet's hydrosphere, assuming it has substantial surface water, would interact with these geological processes in complex ways. Ocean basins might be shallower relative to the planet's size than Earth's ocean basins, as the stronger gravity would cause the seafloor to support less elevation difference from the continents. This could potentially create a world with more extensive but shallower seas, or perhaps a greater number of smaller continents rather than a few large ones. If Kepler-452b formed with a similar water content to Earth, the distribution of that water would be influenced by the planet's topography. The flatter topographic relief caused by stronger gravity might result in smaller elevation differences between the highest and lowest points on the surface, potentially creating more extensive shallow seas and fewer extremely deep ocean basins. Coastal regions might experience less dramatic elevation changes, possibly creating more gradual transitions between land and sea. Seismic activity, earthquakes in Earth terminology, would likely be more energetic on Kepler-452b due to the greater tectonic forces at work, though individual events might affect larger areas as seismic waves travel through the more compressed planetary material. The planet's interior would transmit seismic energy differently than Earth's, with potential implications for how energy from quakes is distributed through the planet. The interaction between geological processes and any potential life adds another layer of complexity. On Earth, life has profoundly influenced geological processes, from the great oxygenation event caused by photosynthetic organisms to the formation of vast limestone deposits from marine organisms' shells. If life exists on Kepler-452b, It might similarly influence the planet's geology, potentially accelerating weathering rates, affecting ocean chemistry, or even influencing tectonic activity through effects on surface processes. Impact craters, formed when asteroids or comets strike the surface, would appear different on Kepler-452b than on Earth. The stronger gravity would attract more impactors, potentially resulting in a higher impact rate throughout its history. However, these craters would tend to be shallower and wider than similar impacts on Earth, as the stronger gravity would constrain how much material can be lofted upward during an impact and cause the crater walls to collapse more readily inward. Over time, the more active geological processes would likely erase these craters more quickly than on more geologically quiet worlds like our Moon or Mars. The mineralogy of Kepler-452b might also differ from Earth's in interesting ways. The higher pressures in the planet's interior could create dense minerals that are rare or non-existent on Earth. If the planet formed with a slightly different elemental composition than Earth, which seems likely given the natural variation between star systems, this could result in a different suite of common minerals forming its crust and mantle. These mineralogical differences could affect everything from the types of rocks found on the surface to the efficiency of various geological processes like weathering and heat transfer within the planet. When we consider all these geological factors together, Kepler-452b emerges as a world that would be recognizably Earth-like in having oceans, continents, mountains, and volcanism, yet with distinctive characteristics resulting from its larger size and stronger gravity. These differences wouldn't merely be academic distinctions, but would fundamentally shape the environment and potentially influence any life that might have evolved there. The geology of Kepler-452b, while currently beyond our ability to directly observe, represents one of the most fascinating aspects of this distant world, a tangible expression of the physical forces that shape planets throughout our galaxy. As we consider the hypothetical geology of Kepler-452b and all the other aspects of this remarkable exoplanet we've discussed, it's worth reflecting on what this distant world means for science and human knowledge more broadly. Since its discovery in 2015, Kepler-452b has established itself as more than just another entry in the Exoplanet catalogue. It has become a scientific touchstone that continues to influence multiple fields of study and will likely do so for generations to come. The scientific legacy of Kepler-452b begins with its role in exoplanet classification. As one of the first confirmed super-Earths orbiting in the habitable zone of a Sun-like star, it helped establish this category of planets as a focus for scientific attention. Before Kepler-452b, many habitable zone exoplanets had been discovered around red dwarf stars, but planets in Earth-like orbits around Sun-like stars proved more elusive. Kepler-452b demonstrated conclusively that such worlds exist, validating theoretical models that predicted their occurrence and focusing attention on the search for more such planets. This discovery has influenced the design of subsequent exoplanet missions and telescopes. When scientists and engineers plan new observatories like the James Webb Space Telescope or proposed future missions like the Habitable Worlds Observatory, they specifically consider how these instruments might characterize worlds like Kepler-452b. Technical requirements for these missions, from mirror size to spectroscopic sensitivity, are partly determined by what would be needed to study the atmospheres and properties of planets at Kepler-452b's distance and orbital characteristics. In this way, a single discovery helps shape the development of scientific infrastructure that will serve multiple generations. In the field of astrobiology, Kepler-452b has become a standard reference point for discussions about habitability beyond our solar system. Textbooks, research papers, and conference presentations routinely cite this planet when explaining concepts related to habitable zones, planetary evolution, and the search for life. Its combination of familiar orbital characteristics around a Sun-like star, combined with its super-Earth size, makes it an ideal case study for exploring how variations in planetary properties might influence habitability. Future generations of astrobiologists will likely continue using Kepler-452b as a conceptual benchmark, even as many more exoplanets are discovered. Kepler-452b has also contributed significantly to refining statistical estimates of how common Earth-like worlds might be throughout our galaxy. Before the Kepler mission, astronomers could only speculate about the frequency of potentially habitable planets. The discovery of Kepler-452b and other similar worlds has allowed scientists to calculate that perhaps 20 to 25% of Sun-like stars might host rocky planets in their habitable zones. These estimates continue to be refined as more data becomes available. But Kepler-452b played a crucial early role in establishing these values, which inform our understanding of how commonly the conditions for life might occur in the universe. For planetary scientists, Kepler-452b has stimulated new theoretical work on super-Earth structure and evolution. Its size places it near the boundary where planets transition from rocky super-Earths to gaseous mini-Neptunes, making it particularly valuable for testing models of planetary formation and composition. Research papers exploring topics from interior structure to potential atmospheric composition frequently use Kepler-452b's parameters as inputs for their models. This theoretical work builds our understanding not just of this specific planet, but of an entire class of worlds that have no analogue in our solar system. In educational contexts, from elementary schools to universities, Kepler-452b has become one of the most commonly referenced exoplanets. Its relatively simple narrative, a slightly larger Earth orbiting in the habitable zone of a star similar to our Sun, makes it accessible even to young students just beginning to learn about astronomy. College textbooks in astronomy and planetary science regularly feature sections on this planet, ensuring that the next generation of scientists grows up familiar with its significance. Educational materials often include artistic renderings of what Kepler-452b might look like, sparking imagination and interest in exoplanet science. The cultural impact of Kepler-452b extends its scientific legacy beyond technical fields into broader public awareness. News coverage of the discovery reached millions of people worldwide, many of whom might otherwise pay little attention to astronomical discoveries. This broader awareness helps build public support for continued investment in space research and exploration, creating a positive feedback loop that enables future discoveries. The planet has been referenced in science fiction, music, art, and other cultural expressions, further cementing its place in our collective imagination. For SETI researchers, Kepler-452b represents not just a data point, but a concrete target that helps focus their search. Radio telescopes have specifically targeted this system, listening for potential signals from a civilization that might have had significantly more time to develop than our own. While no signals have been detected, these observations contribute to our growing database of SETI results, which future generations will continue to analyze with increasingly sophisticated techniques. The focus on specific promising targets like Kepler-452b helps transform SETI from speculative scanning of the skies to a more targeted scientific endeavor. Perhaps most significantly, Kepler-452b has become a symbol in discussions about humanity's long-term future and place in the cosmos. As we face challenges like climate change, resource depletion, and other threats to Earth's habitability, the existence of other potentially habitable worlds provides a cosmic context for our struggles. While Kepler-452b itself lies far beyond our reach with current technology, it and planets like it represent the broader potential of the universe to support life, a potential that extends far beyond our single home world. The scientific legacy of a discovery can be measured partly by how it stimulates new questions and research directions. In this regard, Kepler-452b has been tremendously productive. Its discovery has prompted scientists to ask, how do super-Earths form and evolve? How does increased size affect a planet's potential habitability? What might life look like on a higher gravity world? How common are such planets around different types of stars? These questions have spawned research programs, doctoral dissertations, and entire career trajectories for scientists who might spend decades pursuing the leads that Kepler-452b has provided. The techniques developed to discover and study Kepler-452b have themselves become part of its scientific legacy. The data analysis methods that allowed astronomers to detect its tiny transit signal amid the noise of Kepler's observations have been refined and applied to other datasets, leading to additional discoveries. The statistical tools used to confirm the planet's existence despite limited data have found applications in other areas of astronomy and beyond. These methodological advances represent a less visible but equally important aspect of Kepler-452b's contribution to science. As astronomical techniques continue to advance, Kepler-452b will likely be revisited with increasingly powerful instruments, each observation adding new layers to our understanding of this distant world. Decades from now, scientists might look back on the initial discovery as just the first chapter in a much longer story of gradually revealing the true nature of this planet. In this way, the scientific legacy of Kepler-452b remains open-ended, a gift not just to the present generation of scientists, but to those who will follow, carrying forward the quest to understand our place among the stars. Kepler-452b stands as a milestone in humanity's centuries-long effort to understand the cosmos and our place within it. From the ancient astronomers who first mapped the planets of our solar system to the modern scientists who detected this distant world, each generation has built upon the knowledge of those who came before. Kepler-452b now takes its place in this grand scientific narrative, not an endpoint, but a waymarker on a journey of discovery that will continue long after all of us are gone, inspiring future generations to look up at the stars and wonder what other worlds might wait to be discovered.